Please subscribe to support the channel. The universe is filled with wonders so vast that they often defy human imagination. Among the most striking of these are the colossal stars scattered across our galaxy, monsters of light and energy that make our own sun look small and fragile by comparison. To us on Earth, the sun is the very definition of greatness. It is a giant ball of nuclear fusion, large enough to fit 1.3 million Earths inside of it. Its gravitational grip holds our solar system together, and its radiation gives us life. But as enormous as it seems to us, the sun is a rather ordinary star. Astronomers classify it as a G-type main sequence star, a cosmic middleweight. Now, when we look beyond our solar system, the scale begins to shift dramatically. We encounter stars that make the sun look modest. Betelgeuse, the bright red supergiant in Orion's shoulder, is more than 700 times larger than the sun in radius. Rigel, another star in Orion, outshines the sun by tens of thousands of times in brightness. And then we meet UY Scuti, once measured to be nearly 1,700 times the sun's size. With each discovery, we learn that what seems large to us is merely average or even small on the grand cosmic stage. But even among these stellar titans, there exists a name whispered with awe, VY Canis Majoris. To describe it as large feels like an understatement, almost an insult to its true nature. It isn't just bigger than our sun, it dwarfs every common frame of reference we have. If the sun were a basketball, then VY Canis Majoris would be more like a colossal stadium engulfing entire city blocks. To truly comprehend its size is to stretch the limits of imagination itself. The significance of stars like VY Canis Majoris isn't just in their numbers. It's in the way they bend our sense of scale. When astronomers talk about stellar radii, they're not speaking in miles or kilometers, they're speaking in multiples of the sun itself. It becomes the ruler against which everything else is measured. And while a star 2 or 3 times larger than the sun already sounds impressive, VY Canis Majoris blows past those modest figures, expanding into the category of red hypergiants, stars so swollen and unstable that they're practically in a league of their own. This leads us to the central intrigue. If stars like Betelgeuse, Rigel, and UY Scuti already boggle the imagination, how colossal must VY Canis Majoris be to stand out among them? The answer is staggering, and it redefines our very perception of what a star can be. VY Canis Majoris stands as one of the most extraordinary stars humanity has ever identified. It is not just another red in the night sky, nor merely one more entry in the vast catalogue of stars that astronomers track and study. It is a true outlier, a record breaker, and a symbol of the universe's ability to create objects so immense that they push the limits of our understanding. Nestled within the constellation of Canis Major, the great dog, VY Canis Majoris has long captured the curiosity of astronomers because of its exceptional scale. To say that this star is big is to undersell it. This is a star so large that our sun, impressive as it feels to us here on Earth, becomes an almost negligible speck by comparison. The constellation of Canis Major is itself home to some remarkable stars. It houses Sirius, the brightest star in our night sky, a shining beacon that has guided humans for thousands of years. Yet, hidden deeper in that same constellation, lies a star that does not shine brightly enough to dominate human eyesight but instead makes its mark through its sheer immensity. VY Canis Majoris may not dazzle us with obvious brilliance like Sirius, but what it lacks in visibility, it more than makes up for in its incomprehensible size. Astronomers often call it a red hypergiant, a classification reserved for stars of the most extreme dimensions and volatility. It is widely accepted as one of the largest stars ever discovered. Its title, of course, comes with scientific caution because measuring such giants is not a simple task, and values have shifted as technology has improved. Even so, the consensus remains firm. VY Canis Majoris is absolutely enormous, sitting comfortably in the category of the biggest known stars in the Milky Way galaxy. The very name VY Canis Majoris offers hints at its origins in astronomy. The VY designation stems from its listing as a variable star, meaning its brightness fluctuates over time as seen from Earth. Canis Majoris ties it to its home constellation, the Great Dog, one of the most recognizable star patterns in the southern sky. But despite its placement among familiar stellar neighbors, this giant is not one that can be appreciated without specialized instruments. It is not a household name like Betelgeuse, even though its size eclipses such stars. And yet, for astronomers, The name VY Canis Majoris has become almost legendary, shorthand for the largest of the large. What makes this star's claim to fame so compelling is that it embodies the extreme end of stellar evolution. The Sun, steady and reliable, is often seen as the archetype of a star. But in the Milky Way, the spectrum of stars stretches far beyond that. There are faint red dwarfs that will burn for trillions of years, there are giant blue-white stars that burn hot and fast, and there are massive supergiants that live lives of chaotic instability. Among all these categories, hypergiants are rare. They represent a fleeting stage in stellar life cycles, appearing when a massive star swells to near unthinkable proportions while burning through its fuel in an unstable frenzy. That is the role VY Canis Majoris plays, an icon of cosmic extremes, an object that reminds us of the full diversity of stellar existence. The claim that VY Canis Majoris is one of the largest stars ever discovered is not one of idle exaggeration. It is a conclusion supported by decades of astronomical observation, careful analysis, and refinement of measurements. When astronomers describe a star as being more than 1,000 times larger in radius than the Sun, they are not merely appealing to imagination. They are reporting values derived from observations of its luminosity, its temperature, and the light filtered through its vast surrounding clouds of dust. The results consistently show a star that belongs in the record books. And its location in Canis Major is not just a random point of trivia. It ties this star to the broader structure of our galaxy. Constellations themselves are merely human constructs, patterns drawn across the sky. But they serve as useful maps, giving us reference points to identify where these cosmic behemoths reside. The fact that VY Canis Majoris is in Canis Major means that, despite being 3,900 light-years away, its light reaches us from the direction of that constellation, linking one of the greatest stellar giants to a familiar piece of the heavens. To summarize this claim in its most distilled form, among the billions upon billions of stars in our galaxy, VY Canis Majoris is one of the largest ever discovered. It is not the brightest in the night sky, not the most massive, and not the most famous, but in sheer volume, it towers over nearly all others. If astronomy had a hall of fame for stars, VY Canis Majoris would be placed on a pedestal reserved for the very few that redefine the limits of possibility. Its position in the constellation Canis Major grounds it in our maps of the sky, but its immense size elevates it to legendary status among the giants of the cosmos. The power of this claim lies not just in the numbers but in what those numbers represent, an encounter with scale so vast that it challenges our ability to comprehend it. VY Canis Majoris is not simply another pinprick of light, it is a window into the grandeur of stellar extremes, an enduring symbol of the idea that somewhere out there, beyond our ordinary perceptions, the universe is creating things of unimaginable magnitude. What does a star this gigantic really look like? And how do we even know its size? It's a question that doesn't just spark curiosity, it forces us to confront the very limits of what human observation and imagination are capable of. When we hear the phrase, one of the largest stars ever discovered, our minds naturally want to picture it. We might imagine an enormous glowing sphere of fire, like our Sun, only stretched 1,000 times larger. But the reality of VY Canis Majoris is far stranger, far more dramatic, and far more awe-inspiring than that simple picture suggests. If you were to stand on some imaginary vantage point, far enough away that you could take in the full breadth of VY Canis Majoris, you wouldn't see a neat, perfect orb of light like the Sun. Instead, you would see a bloated, misshapen, and turbulent star, surrounded by vast clouds of gas and dust that it has hurled off into space during violent eruptions. Its surface wouldn't appear smooth or symmetrical. It would be mottled, with colossal convective cells, huge upwellings of plasma, each one larger than Earth itself, shifting and boiling across its outer layers. Unlike the brilliant golden white of our Sun, VY Canis Majoris glows with a deep reddish hue, the mark of its cooler surface temperature and its status as a red hypergiant. But how can we, sitting here on Earth nearly 3,900 light-years away, claim to know any of this? The light we see from VY Canis Majoris left that star during the Bronze Age on Earth, when humans were still carving out the earliest chapters of civilization. By the time it reaches us, that light has been dimmed and filtered by interstellar dust, obscured by the vast distance it has traveled. To the naked eye, the star doesn't look like anything spectacular at all. It's faint, easily overlooked, and hidden in the crowded background of its constellation. It takes the ingenuity of telescopes, the refinement of astronomical instruments, and the patience of careful observation to peel back the layers and reveal what lies at the heart of that dim glow. Astronomers use several methods to probe the size of such a gigantic star. One of the most important is interferometry, a technique where light gathered by multiple telescopes is combined to create the resolving power of a much larger instrument. This allows scientists to measure tiny angular diameters across the sky, fractions of a degree, that correspond to actual sizes when multiplied by the star's distance. Another tool is spectroscopy, which analyzes the starlight itself. By studying the absorption and emission lines within the spectrum, astronomers can determine the star's temperature, chemical composition, and how much dust is surrounding it. From those values, they can model the star's radius and luminosity. And then there are the nebulae, the clouds of gas and dust that VY Canis Majoris has ejected into its surroundings. Observing these expanding shells provides further clues about the star's behavior, its history of violent eruptions, and its approximate size. In fact, much of what makes VY Canis Majoris visually remarkable isn't just the star itself but the chaotic environment it has created around it, a vast shroud of material glowing faintly in the infrared and radio wavelengths. So, what does it look like? It looks like chaos frozen in slow motion. It looks like a dying giant struggling against the laws of physics, shedding its mass in a desperate attempt to stabilize itself, but knowing that its life is nearing an inevitable and explosive end. It doesn't shine steadily like our sun. It flickers, it varies, it breathes in light and darkness across years and decades. Its outer layers are unstable, swollen to such extremes that gravity is only barely able to hold them together. In photographs captured by the Hubble Space Telescope and ground-based observatories, it appears not as a neat circle but as a distorted, irregular object with sprawling tendrils of material reaching outward, like a cosmic octopus stretching across space. And yet, despite all this advanced observation, despite decades of study, the question of exactly how large VY Canis Majoris remains tricky. Astronomers revise their estimates as better instruments become available. For years, it was thought to be the absolute largest star ever known, with early estimates placing its radius at nearly 3,000 times that of the Sun. More recent and refined measurements suggest that it is smaller than that, but still massive enough to rank among the biggest. This uncertainty doesn't diminish its grandeur. If anything, it adds to the mystery, reminding us that even with the best tools at our disposal, there are limits to what we can know about an object so far away and so extreme in nature. So when we ask, what does a star this gigantic look like? The answer is both scientific and poetic. Scientifically, it looks like a vast, bloated red hypergiant enshrouded in dust and gas, glowing dimly with the reddish light of a cooling surface, surrounded by the wreckage of its own eruptions. Poetically, it looks like a living monument to the grandeur of the universe, an object so large and unruly that it challenges us to rethink the boundaries of what a star can be. And when we ask, how do we even know its size? The answer points to the triumph of human ingenuity. It is through the careful piecing together of clues, through light, spectra, distances, and models, that we can say with confidence, VY Canis Majoris is among the largest stars ever discovered, a true colossus of the cosmos. The fact that we can even ask and attempt to answer such a question is itself a marvel, a testament to the human drive to understand the incomprehensible. The historical story of VY Canis Majoris is one of those fascinating tales where something almost hidden in plain sight eventually reveals itself to be extraordinary. For much of human history, this star was not considered remarkable at all. It wasn't one of the dazzling jewels that ancient civilizations charted into mythologies, nor was it bright enough to dominate the night sky like Sirius or Betelgeuse. To early stargazers without telescopes, VY Canis Majoris appeared only as a faint reddish point, easily lost among the glittering backdrop of the Milky Way in the constellation Canis Major. Yet hidden behind that unassuming appearance was one of the largest stars ever discovered, patiently waiting for the right tools and the right observers to uncover its secrets. The first documented mention of VY Canis Majoris in astronomy comes from the 19th century. In 1801, it was included in the star catalogue compiled by Jerome Lalande, a French astronomer who carefully mapped thousands of stars. At the time, VY Canis Majoris was classified without any particular fanfare. It wasn't immediately recognized as anything unusual beyond the fact that it appeared as a faint star in the rich star fields of Canis Major. In those early records, it was simply another entry, identified, catalogued, and left largely unexplored. No one suspected that the star was hiding such an immense scale. The real turning point came later, as telescopes improved and astronomers began to study variable stars more closely. VY Canis Majoris was recognized as a semi-regular variable star, meaning its brightness fluctuated when viewed from Earth. This variability hinted at something interesting. Stars that flicker or change in brightness often harbor secrets: pulsations, eruptions, instability, or surrounding clouds of material. By the late 19th and early 20th centuries, astronomers began to note that VY Canis Majoris wasn't just faint and red, it was peculiar. It didn't behave like an ordinary star. As photographic plates and spectroscopy became more widely used in the early 20th century, the strangeness of VY Canis Majoris became even clearer. Its spectrum revealed features consistent with a cool, massive, late-type star, confirming that it was a red supergiant or hypergiant. By studying its spectrum, astronomers could tell that it had an enormous, swollen outer atmosphere and that it was shedding material into its surroundings. At the time, however, astronomers did not yet have the precise tools to measure its true size. Even so, they began to suspect that it belonged in the category of stellar giants. What really made VY Canis Majoris remarkable in a historical sense is how much it challenged astronomers' expectations once better instruments came into play. In the mid-20th century, observations using larger ground-based telescopes suggested that this star wasn't just a little unusual. It might actually be one of the largest known stars. By the 1970s and 1980s, more precise studies revealed the massive nebula of gas and dust surrounding it, ejected during its violent eruptions. This wasn't just a red supergiant quietly burning its fuel, it was a chaotic hypergiant throwing off material on a staggering scale. The discovery of this nebula surrounding VY Canis Majoris was a revelation. It demonstrated that the star wasn't simply large, it was unstable, active, and nearing the end of its stellar life. The Hubble Space Telescope later added even more detail to the picture. In the early 2000s, images taken with Hubble revealed just how complex and asymmetric the environment around VY Canis Majoris really was. Instead of a smooth, spherical shell of gas, the star was surrounded by vast clumps and arcs of material, stretching trillions of kilometers across space. These observations confirmed what earlier astronomers had begun to suspect. VY Canis Majoris wasn't just unusual, it was extraordinary. It became clear that this faint red star, first noted without much excitement in the 1800s, was in fact one of the largest and most violent stars in our galaxy. Part of what makes its historical context so intriguing is that it's a story of gradual revelation. Unlike stars such as Betelgeuse, which have always stood out for their brightness and prominence, VY Canis Majoris had to earn its reputation through patient study. For more than a century, it was considered nothing special, until new technologies peeled back its outer layers and revealed a giant beyond imagination. Today, its name is synonymous with enormity, but that fame was not instant. It was the product of persistent curiosity and the steady progress of astronomy, moving from simple catalogues to sophisticated telescopes and instruments that can analyze the universe in wavelengths invisible to the human eye. What astonished astronomers, and continues to, is how deceptive the star's appearance is. To the naked eye, it's forgettable. To the telescope, it's a behemoth. That tension between invisibility and enormity is part of why VY Canis Majoris remains such a powerful symbol in astronomy. Historically, it teaches us that appearances in the cosmos can be deeply misleading, and that even the faintest points of light can conceal mysteries larger than we ever imagined. When we talk about VY Canis Majoris being about 3,900 light-years away from Earth, we are immediately dealing with distances that break ordinary comprehension. A light-year is the distance that light, traveling at 299,792 kilometers per second, the ultimate cosmic speed limit, covers in a single year. That's nearly 9.5 trillion kilometers, or about 5.9 trillion miles. Now, multiply that by 3,900. The light that leaves VY Canis Majoris takes nearly 4 millennia to reach us, crossing a gulf of space so vast that our entire recorded human history is shorter than the time it takes a single photon to make that journey. When the light we see today left the star, ancient civilizations on Earth were in their infancy. Empires had not yet risen, pyramids had not yet been built, and countless generations of humans lived and died before that light finally entered our telescopes. This distance matters enormously for how we observe the star, and how much we can know about it. For one, even though VY Canis Majoris is one of the largest stars ever discovered, it does not appear bright to our eyes. At 3,900 light-years away, its immense size and luminosity are diminished by sheer distance. To us, it is faint, almost inconspicuous, requiring careful observation with telescopes to even be studied in detail. If it were only a few hundred light-years away, it might dominate our sky with its red glow, possibly even becoming a cultural icon like Betelgeuse or Antares. But at thousands of light-years, it's buried in obscurity, hiding behind dust clouds and distance. Another reason this distance is so important is that it complicates measurements. When astronomers try to determine the size of a star like VY Canis Majoris, they need two key pieces of information: how bright the star actually is, its intrinsic luminosity, and how far away it is. But distance measurements are notoriously tricky in astronomy, especially for objects thousands of light-years away. Errors in estimating distance translate directly into errors in estimating size and luminosity. If a star is thought to be farther away than it actually is, astronomers might conclude it is larger and brighter than it really is. Conversely, if it's closer than believed, its true scale might be smaller. The difficulty of measuring distances to stars like VY Canis Majoris is part of the reason why its size estimates have changed over time. For decades, astronomers worked with less precise measurements, leading to claims that it might be nearly 3,000 times the Sun's size. Later, with the help of missions like Hipparcos and Gaia, which specialize in measuring stellar parallax, the tiny apparent shift of a star's position in the sky as Earth orbits the Sun, scientists were able to refine its distance more accurately. That revision brought new, more realistic estimates of its size. Still enormous, still among the largest, but not quite as extreme as once believed. Its location also has observational consequences because of the interstellar medium. VY Canis Majoris lies in a region of the Milky Way that is relatively dense with dust and gas. This dust absorbs and scatters some of the light that reaches us, making the star appear dimmer and redder than it actually is. Astronomers call this effect extinction, and it complicates efforts to measure the star's true luminosity and temperature. By analyzing how much of the star's light has been filtered, astronomers can make corrections, but these adjustments add another layer of uncertainty. And then there's the sheer scale of what it means to be 3,900 light-years away. That distance ensures that any changes happening at VY Canis Majoris are ancient history by the time we see them. If the star had gone supernova yesterday, we wouldn't know about it for nearly 4,000 years. The light carrying that news is still in transit, crossing the interstellar void. In other words, when we study VY Canis Majoris, we are looking into the past, seeing the star not as it is now, but as it was during Earth's Bronze Age. In a sense, astronomy always deals with history, but with stars at these kinds of distances, the historical aspect is amplified to staggering levels. This enormous gap between us and the star also sets the stage for why discoveries about it feel so powerful. To uncover details about something that far away is a testament to the reach of human technology and curiosity. Telescopes, spectrographs, and space-based observatories allow us to bridge that gulf of time and space, teasing out details from faint signals. Every measurement, its variability, its spectrum, its surrounding nebula, represents data that has crossed thousands of years and trillions of miles just to reach us. The fact that we can turn those faint whispers of light into knowledge about one of the galaxy's largest stars is nothing short of remarkable. So why does the distance matter so much? Because it defines both the challenge and the wonder. The challenge lies in how faint, distorted, and ancient the signals are by the time they arrive. The wonder lies in the fact that, despite all this, we can still study VY Canis Majoris in meaningful detail. It's distant enough that its light is older than human civilization, yet close enough that we can detect its instability, its eruptions, its surrounding nebula, and even refine its measurements over time. It reminds us that astronomy is the science of patience and perspective, of drawing profound truths from faint glimmers across unimaginable distances. When astronomers first turned their telescopes toward VY Canis Majoris, what they saw was far from extraordinary. It wasn't a dazzling beacon like Sirius, which sits in the same constellation and has guided sailors and storytellers for thousands of years. Instead, VY Canis Majoris looked faint, almost disappointing. Even with the telescopes of the 18th and 19th centuries, which were revolutionary for their time, It appeared as nothing more than a small, reddish point of light, dim, unassuming, and easily overlooked in the rich star fields of Canis Major. Nothing in those early glimpses betrayed the fact that this faint glow belonged to one of the largest stars in the galaxy. To put this in perspective, telescopes of that era lacked the resolution and sensitivity needed to do more than magnify and record what the human eye already saw. The star's faintness, caused by both its enormous distance and the interstellar dust that filtered its light, made it seem like an ordinary, if somewhat reddish, member of the Milky Way. Early astronomers catalogued it simply because it was there, another star to add to the growing lists of objects in the sky. Its variability, the slight changes in brightness that set it apart, were not immediately recognized, and without the advantage of modern spectroscopy, its true nature as a swollen red hypergiant remained completely hidden. The reddish hue of VY Canis Majoris, however, did catch some attention. Astronomers in the 19th century noted that it wasn't white or blue like so many bright stars, but rather faintly tinted, a sign of a cooler temperature. At the time, though, the science of stellar classification was still in its infancy. The link between color, temperature, and size was not well understood. A reddish tint simply meant cooler compared to bluer stars, but it didn't reveal the monstrous radius that lay behind that light. To early observers, it was just another cool star in a sky filled with countless others. One of the reasons VY Canis Majoris remained underestimated for so long is because of how deceptive faint stars can be. To the naked eye and through small telescopes, brightness is often equated with importance. Bright stars attract study, faint stars are catalogued and passed over. Yet brightness can be misleading. A star can be faint not because it is small or insignificant, but because it is so far away, or because its light has been dimmed by intervening cosmic dust. VY Canis Majoris is a perfect example of this deception. In truth, its luminosity dwarfs the Sun's many times over, but from Earth, 3,900 light-years away, it barely registers to casual stargazing. As telescopes improved through the late 19th and early 20th centuries, astronomers began to notice that VY Canis Majoris was not entirely stable. Photographic plates revealed that its brightness varied, sometimes subtly, sometimes dramatically. It was added to the growing list of variable stars, a category of stellar objects that fascinated astronomers because variability hinted at deeper physical processes. Even then, though, the star was not treated as extraordinary. It was considered peculiar, yes, its irregular changes of brightness made it worth noting, but few suspected they were dealing with a star of galactic record-breaking proportions. Spectroscopy, when it finally became applied to stars like VY Canis Majoris, began to unravel its secrets. By splitting the faint reddish light into its component wavelengths, astronomers could detect absorption lines that betrayed its cooler temperature and hinted at an enormous, tenuous outer atmosphere. Still, without accurate distance measurements, they had no way of translating those spectral clues into real-world size. They knew it was a massive star, a giant among giants, but they didn't yet understand just how far it extended. From earthbound telescopes, even well into the 20th century, VY Canis Majoris remained a point of light surrounded by faint nebulosity. Astronomers could not see the star's actual surface. It was too far away, and its size, however immense, still translated to the tiniest fraction of an arc-second on the sky. What they saw instead was a reddish dot embedded in faint smudges of gas and dust, a hint of the violent outbursts that would later be confirmed as part of its hypergiant nature. To the untrained eye, it would have seemed unremarkable. To the trained astronomer, it was unusual, but not yet fully understood. This stage in its observational history is fascinating because it underscores how astronomy is shaped not just by the objects in the universe, but by the tools we use to study them. For centuries, VY Canis Majoris looked like little more than a faint star. Only when the tools of measurement and analysis improved did its true identity begin to emerge. Early telescopes gave us the faint reddish dot. Spectroscopy revealed it was a cool giant. Nebular imaging showed it was unstable and shedding mass. Eventually, advanced interferometry and space telescopes would place it among the largest stars ever known. The story of those early observations serves as a reminder: the universe doesn't always shout its wonders. Sometimes, the most extraordinary phenomena masquerade as the ordinary, waiting for patient eyes, better technology, and sharper minds to uncover their significance. VY Canis Majoris spent decades, even centuries, as an overlooked faint point in Canis Major, until astronomy caught up with its reality. The star had always been a giant, it simply took humanity time to recognize it. When we begin to talk about the sheer size of VY Canis Majoris, the numbers themselves almost lose meaning. Astronomers estimate its radius to be about 1,400 times that of the Sun. At first glance, that figure seems straightforward, but it takes a bit of imagination to understand just what it really implies. Our Sun, which feels unimaginably huge to us on Earth, is already a monster in its own right. You could line up 109 Earths side by side across the Sun's diameter. Yet, VY Canis Majoris stretches that scale so far beyond familiarity that even seasoned scientists pause at the immensity of it. The Sun has a radius of about 696,000 kilometers, or roughly 432,000 miles. Multiply that by 1,400, and VY Canis Majoris reaches a radius of nearly 1 billion kilometers. That's not just larger than the Sun, it's larger than the orbits of the inner planets of our solar system combined. To put it in more direct terms, if you were to place VY Canis Majoris where our Sun currently sits, its surface would engulf Mercury, Venus, Earth, and Mars. Without hesitation. The star would not just swallow them, it would extend far beyond, stretching out close to the orbit of Jupiter. The asteroid belt, home to Ceres and Vesta and countless rocky remnants of planetary formation, would be buried deep inside the star's bloated outer atmosphere. Think for a moment about Earth in this scenario. Our planet sits at a comfortable 150 million kilometers from the Sun, a distance we call 1 astronomical unit. It's just right for liquid water, stable climates, and life as we know it. If VY Canis Majoris were at the center of our solar system, Earth would not exist as a solid planet. It would be scorched, disintegrated, and vaporized inside the star's outer layers. Even Mars, that distant rusty desert, would find itself swallowed whole. Life in our solar system, in such a scenario, would be completely impossible. For another comparison, Jupiter orbits the Sun at about 778 million kilometers. VY Canis Majoris would stretch nearly to this orbit. That means our largest planet, a gas giant itself so big that more than 1,300 Earths could fit inside it, would sit dangerously close to being engulfed. Only Saturn, orbiting farther out at 1.4 billion kilometers, would be truly safe. This mental exercise shows just how massive the star really is. It would dominate our solar system to such an extent that only the outer gas giants would remain beyond its reach. To put the star's size in terms more tangible than planetary orbits, consider speed. A passenger airplane travels at about 900 kilometers per hour. At that speed, you could circle Earth in less than 2 days. But if you tried to fly around the circumference of VY Canis Majoris, it would take you more than 1,000 years of continuous flying, without ever stopping, just to complete one lap. Even light itself, which can circle Earth more than 7 times in a single second, would need over an hour to make the same journey around VY Canis Majoris. Think about that. The fastest thing in the universe, the very speed limit of nature, slowed to over an hour just to travel around one single star. Another striking comparison is with Betelgeuse, the famous red supergiant in Orion. Betelgeuse has an estimated radius about 764 times that of the Sun, already a staggering figure. Yet VY Canis Majoris nearly doubles that size, towering over even one of the most famous giant stars in our sky. And compared with Rigel, the brilliant blue supergiant also in Orion, VY Canis Majoris may not shine as brightly in visible light, but its bulk dwarfs Rigel's in terms of sheer physical dimensions. What makes the size of VY Canis Majoris even more remarkable is the way it plays with human intuition. Our minds aren't built to grasp billions of kilometers, so we fall back on analogies. If the Sun were reduced to the size of a beach ball, Earth would be a tiny pea orbiting about 25 meters away. In that same model, VY Canis Majoris would balloon to the size of a massive sports stadium, engulfing every nearby object in its colossal presence. It is less like comparing a car to a truck and more like comparing a grain of rice to an entire mountain range. And yet, despite being so large in radius, VY Canis Majoris doesn't hold the crown for mass. Its immense bulk comes from its swollen, extended outer layers, which are tenuous and unstable. In terms of sheer physical footprint, though, it is a king among stars. The concept that one single star could stretch almost to Jupiter's orbit if placed in our solar system is so staggering that it forces us to confront the true scale of the cosmos. The Sun feels dominant to us because it is our source of light and life, but in the greater cosmic theater, it becomes almost laughably small compared to titans like VY Canis Majoris. When astronomers describe this star's radius as 1,400 times the Sun's, they are not merely presenting a statistic. They are inviting us to reframe our entire sense of scale. This is not just an object, it is a cosmic leviathan, so large that it reshapes our imagination of what a star can be. It is a reminder that in the Milky Way, even something as central to our existence as the Sun is not exceptional, but one small piece of a much grander puzzle. When we talk about how many suns could fit inside VY Canis Majoris, we're really talking about a comparison of volumes, because no one is literally stacking stars like billiard balls. Volume is the key, and volume scales like the cube of size. That single detail, the cube, is why giant stars leave our intuitions in the dust. If VY Canis Majoris has a radius around 1,400 times that of the Sun, you don't just multiply the Sun's volume by 1,400. You multiply by 1/400 cubed. And 1/400 cubed is a monstrous number, about 2.7 billion. In other words, by volume, VY Canis Majoris could hold on the order of 2.7 billion suns. Let's unpack that slowly. The Sun's radius is roughly 696,000 kilometers. Using 1,400 times, that gives a characteristic radius for VY Canis Majoris of nearly 1 billion kilometers. The volume of a sphere is /frac 4/3 /pi r cubed. So when you scale the radius by a factor of 1,400, the volume balloons by 1,400⁻³ /approx 2,744,000,000. That means the star's interior space, if we treat it like a sphere with that characteristic radius, has around 2.7 billion times more room than the Sun's interior space. This is not a gentle increase, it's a runaway explosion of scale. Even for people comfortable with big numbers, billions of suns is hard to feel. One way to place it is to recall a famous stat you may have heard: roughly 1.3 million Earths could fit inside the Sun by volume. Multiply that by about 2.7 billion, and you get on the order of 3.5 quadrillion Earths that could fit inside VY Canis Majoris by volume equivalents. Quadrillions are numbers we almost never encounter in daily life. They belong to the cosmic ledger, not the household budget. Now, a critical technical caveat that makes this comparison honest and informative. These are volume equivalence comparisons, not physical packing scenarios. Stars are not rigid balls, and you cannot pack suns inside another star. The phrase "how many suns could fit" is shorthand for what multiple of the Sun's volume does this star have. Moreover, VY Canis Majoris is not a solid bounded sphere with a crisp surface. Like all red hypergiants, its outer layers are puffed up, tenuous, and turbulent. Its envelope is a froth of convective cells, shock waves, and outflows. The boundary between star and space is fuzzy. So while the factor of 2.7 billion provides an excellent sense of scale, it sits atop a real astrophysical complexity. The outermost layers are so thin that, in places, a cubic centimeter of gas might contain far, far fewer particles than air in a high-altitude laboratory on Earth. This brings us to density, which is where the story becomes counterintuitive. If a star's radius increases dramatically while its mass does not keep pace, the average density plunges. The Sun's average density is about 1.41 grams per cubic centimeter, denser than water. A red hypergiant like VY Canis Majoris might have a mass only a few tens of times the Sun's, not billions of times. If you take, for illustration, a mass around a couple dozen suns and spread it through a volume billions of times larger, the average density falls to a whisper of the Sun's density, tiny fractions of a gram per cubic centimeter, down to values that, in the outermost layers, are closer to a laboratory vacuum than to any intuitive notion of stuff. That's why hypergiants can be so ballooned. Radiation pressure, low gravity at the extended surface, and vigorous convection lift their atmospheres outward until the envelope is sprawling and delicate. This low-density reality also explains why volume should not be conflated with bigness in the sense of gravitational dominance. The Sun's central gravity would utterly outweigh any rock you could hold in your hand, but VY Canis Majoris' swollen photosphere is so far from its core that surface gravity there is feeble by stellar standards. The star is large in extent but loose-knit, like a gigantic cosmic fog bank lit from within. The envelope is susceptible to pulsations, eruptions, and mass loss events that literally resculpt the star's silhouette over time. That changeability also complicates where we draw the line for radius, and thus for volume comparisons. Depending on the wavelength observed, visible, infrared, radio, and how much dust and gas are in the way, the edge of VY Canis Majoris can look different. But even within generous uncertainty bands, the volume comparison stays in the billions of suns ballpark, not millions, not tens of millions, billions. Let's tether the math to a few intuitive touchstones. Suppose you could hollow out a sphere the size of VY Canis Majoris and start dropping suns into it as evenly spaced points, just as a thought experiment. After you had placed 2 suns, you'd have scarcely begun. 2,000? Still nothing. 2 million? You wouldn't notice any filling. 2 billion? Now we're in the right order of magnitude. Only around 2.7 billion suns later would the tally match the star's volume. Even then, because spheres don't tile space perfectly, there are packing fractions to consider, the rhetorical fit would be different from the pure volume ratio. But the point stands. We are so far beyond day-to-day scales that even the word billion struggles to carry the weight. Comparisons to the inner solar system lend another angle. Earlier we noted that a radius near 1,400 solar radii brings the surface out toward Jupiter's orbit. Think about the gulf from the Sun to Earth, 1 astronomical unit. If you turn that distance into a radial ruler inside VY Canis Majoris, Earth's orbit would lie deep in the interior. The volume contained within Earth's orbit, \frac 423 \pi 1 \text au ⁻3 would be a tiny fraction of the star's full volume, because the star's radius extends far beyond $1 Australian. And since volume scales with the cube of radius, when you compare the star's full radius to Earth's orbital radius, the total interior volume skyrockets. That cubic scaling is the villain, or hero, behind the incomprehensible count of how many suns. Another insightful comparison. Think about time rather than space. Light travels 300,000 kilometers every second. It zips around Earth in under 1/10 of a second and traverses the Sun's diameter in a little over 4 seconds. But to go around the circumference of a sphere with radius near 1 billion kilometers, light needs more than an hour. That's a dynamic way to feel the bloat of the star. If the fastest thing in the universe takes an hour to do a lap around one star, then saying billions of suns by volume stops sounding like hyperbole and starts sounding conservative. These volume numbers also hint at why hypergiants have such spectacular winds and circumstellar nebulae. The energy output from fusion in their cores must diffuse through a staggeringly vast and low-density envelope. Radiation pressure and convection churn this envelope, and with surface gravity so weak, material can be lofted outward and escape. Over thousands of years, that slow, steady bleed, and occasional violent ejection, carves out arcs, knots, and fans of gas and dust that we can actually image. The very bigness that grants the star its 2.7 billion suns volume is the same bigness that makes it fragile and leaky at the edges. It's worth addressing how updated observations influence the how many suns figure. Because radius estimates have evolved with improved distance measurements and better modeling of dust extinction, you'll see a range of published values for VY Canis Majoris radius. If the true radius is a bit smaller than 1,400 solar radii, the volume ratio falls accordingly. If it's larger, the ratio grows. But the cube law's brutality keeps the answer in a regime that's still staggering. For instance, even trimming the radius to 1,200 solar radii drops the volume factor to about 1.7 billion suns, still well beyond any comfortably graspable number. Push it up toward 1,600 and you're over 4 billion. The exact count shifts, but the headline stands, billions, plural. When we frame how many suns fit inside, we're really crafting an on-ramp for the mind to enter cosmic scale. The sun is our most familiar stellar yardstick. If a star can hold billions of suns by volume equivalence, that tells us it occupies not just another category but another continent on the map of stellar possibility. It also underscores an important astrophysical moral. Size, mass, and brightness are related but distinct. VY Canis Majoris wins in sheer volume, but it is not the most massive star, nor the most luminous across all wavelengths, nor the hottest. The star is a champion in one arena, the breadth of its envelope, because of an evolutionary moment near the end of a massive star's life where physics spreads matter thin and wide. Finally, let's loop this back to what you see at the eyepiece. You won't ever look up and visually sense billions of suns. You'll see a modest, reddish variable star, dimmed by dust and distance. The fact that such a modest-looking point corresponds to a sphere so big that it could contain billions of suns by volume is a perfect emblem of astronomy's central magic. Appearance is not reality at cosmic scales. The numbers, when properly interpreted, reveal a reality so outsized that our language huffs and puffs to keep up. When discussing VY Canis Majoris, it's very tempting to conflate size with mass, because in everyday experience the two tend to go hand in hand. A bigger building is heavier, a larger ship weighs more, and a mountain outweighs a hill. But stars, especially hypergiants like VY Canis Majoris, play by different rules. This is where one of the most fascinating paradoxes of astronomy reveals itself. VY Canis Majoris is gargantuan in terms of volume, but it is not the most massive star in the universe, not even close. The mass of VY Canis Majoris is generally estimated to be somewhere between 17 and 25 times the mass of the Sun. That is certainly impressive by our standards, but it pales in comparison to other stellar titans. Stars such as a 136A1, located in the Tarantula Nebula in the Large Magellanic Cloud, are estimated to have masses upward of 150 to 200 times that of the Sun. That means there are stars nearly 10 times more massive than VY Canis Majoris. Yet despite their crushing gravitational pull and searing energy output, those stars are physically smaller in diameter. They're dense, compact, and intensely bright, unlike the sprawling puffiness of VY Canis Majoris. This distinction between mass and size is crucial. Mass dictates how much material a star has, which in turn governs how strong its gravity is, how hot its core burns, and how fast it consumes its nuclear fuel. Size, on the other hand, especially in the case of red hypergiants, is a result of how the star's outer layers respond to internal processes. When massive stars age, their cores contract as they fuse heavier elements, but their outer envelopes expand outward dramatically. The gravitational grip at the surface weakens, the outer layers balloon, and the result is a star with a huge volume but relatively low density. To get a sense of the density contrast, let's compare. The Sun's average density is about 1.41 grams per cubic centimeter, denser than water. A red hypergiant like VY Canis Majoris, despite being many times more massive, spreads that mass over volume billions of times larger. The result is an average density that is lower than air in Earth's atmosphere, in some layers comparable to a laboratory vacuum. This is why it can appear paradoxical. A star with only a few dozen solar masses is somehow swollen to a radius that stretches nearly to Jupiter's orbit. This is also why VY Canis Majoris is so unstable. Its sheer size isn't backed up by proportionate mass. Think of it as a giant, inflated balloon compared to a compact iron sphere. One is big but fragile, the other small but unyielding. VY Canis Majoris is like that balloon. Its envelope is so extended and tenuous that it sheds mass easily in powerful stellar winds and eruptions. It doesn't have the tight gravitational grip of a smaller, denser massive star, so its outer layers are constantly leaking into surrounding space. Now, consider the stars that are truly massive, like the blue hypergiants and Wolf-Rayet stars. These stars might pack more than 100 suns worth of mass into volumes only a few dozen times larger than the Sun. Their gravity is crushing, their luminosity blinding, and their temperatures ferociously high. They look nothing like the cool, distended red glow of VY Canis Majoris. In fact, if you were to place a 136A1 and VY Canis Majoris side by side, the former would outweigh the latter several times over, but VY Canis Majoris would dwarf it in size, stretching out like an enormous red cloud. This separation of mass and size also helps explain why VY Canis Majoris is nearing the end of its life. More massive stars like a 136A1 will burn through their fuel quickly and die spectacularly, but while they live, they hold themselves together tightly. VY Canis Majoris, with its modest mass compared to its size, is already on the verge of collapse, its envelope unstable and fragile. Its lower mass relative to its swollen volume means that its core cannot indefinitely support the outer layers, which is why astronomers believe it's headed for a dramatic end as a supernova or possibly even a direct collapse into a black hole. The distinction between mass and size is a lesson in the deceptive nature of appearances. If you were to rank stars by bigness, VY Canis Majoris would sit near the top. If you were to rank them by mass, however, it would fall far down the list, overshadowed by dozens of blue supergiants, Wolf-Rayet stars, and luminous giants that are smaller in radius but much heavier in actual material. This is why astronomers often stress that largest and most massive are two very different titles in the cosmos. So when people ask whether VY Canis Majoris is the biggest star, the answer depends on what you mean by big. In terms of volume, yes, it is one of the largest stars ever observed. In terms of mass, no, it's far from the champion. This duality is part of what makes it so fascinating. It forces us to separate our intuitive sense of size and weight and to rethink what large really means in an astrophysical context. It also highlights the diversity of stellar evolution. Not all massive stars swell into hypergiants like VY Canis Majoris. Some evolve differently, staying hot and compact until their end. VY Canis Majoris just happens to be one of those stars that has expanded to an extraordinary extent, creating a cosmic spectacle in size if not in raw mass. And this paradox is not a mere curiosity, it has real implications. The relatively low mass compared to its size makes the star unstable, prone to shedding matter, and destined to collapse sooner rather than later. That is why astronomers keep such a close eye on it. It may not hold the crown for mass, but in terms of teaching us how stars live and die, VY Canis Majoris is every bit as important as the true heavyweights of the universe. When it comes to brightness, VY Canis Majoris once again demonstrates how deceptive the cosmos can be. In sheer luminosity, this red hypergiant outshines our Sun by an incredible factor. Estimates place its luminosity at anywhere between 200,000 to 300,000 times greater than that of the Sun. That means if you could line up 200,000 suns next to each other and combine all of their light, VY Canis Majoris would still be shining just as brightly on its own. That number is staggering. It's a reminder that we are not dealing with just a big star, but an energy engine on a nearly incomprehensible scale. Now, consider what that luminosity means in human terms. The Sun provides all the heat and light that sustains life on Earth from 150 million kilometers away. If VY Canis Majoris were placed in its stead, the flood of radiation would sterilize Earth instantly, not just because of its sheer size swallowing our orbit, but because its radiant energy output is overwhelmingly greater. The concept of a habitable zone would cease to exist within hundreds of millions of kilometers, as the searing light and heat would vaporize any possibility of life. But here comes the paradox. If VY Canis Majoris is hundreds of thousands of times more luminous than the Sun, why doesn't it blaze like a beacon in our night sky? Why does it appear faint, only visible with the aid of telescopes or under very dark skies? The answer lies in two crucial factors: distance and dust. First, distance. VY Canis Majoris sits about 3,900 light-years away from us. In cosmic terms, that's still within our galactic neighborhood, but for the human eye, it is far beyond the realm of naked eye brilliance. Light obeys what astronomers call the inverse square law. Its apparent brightness diminishes as the square of the distance increases. So even though VY Canis Majoris is staggeringly luminous, the vast gulf of space between us and the star reduces its apparent brightness to a mere whisper by the time it reaches Earth. By contrast, Betelgeuse, another red supergiant, is only about 640 light-years away, much closer than VY Canis Majoris, and that proximity makes Betelgeuse easily visible as a bright red point in Orion's shoulder. Second, dust. VY Canis Majoris is surrounded by thick clouds of gas and dust that it has expelled over centuries of violent eruptions and steady stellar winds. These clouds absorb and scatter visible light, making the star appear far dimmer than its true power. Much of its radiant energy is re-emitted in the infrared part of the spectrum, which the human eye cannot detect. To our sight, VY Canis Majoris looks like a faint, reddish smudge in the constellation Canis Major, far less impressive than its actual luminosity suggests. Telescopes that can observe in infrared, however, reveal its true brilliance, piercing through the veils of dust to uncover the colossal energy output that optical wavelengths conceal. The combination of distance and dust means that VY Canis Majoris is not one of the spectacular stars you can simply step outside and point to in the night sky. Without specialized instruments, You would never guess that it is among the most luminous stars in the galaxy. This is one of the humbling truths of astronomy. Appearance can be radically misleading. A faint dot seen through a telescope can, in reality, be a powerhouse so radiant that it dwarfs our sun hundreds of thousands of times over. Astronomers use luminosity as a more accurate measure of a star's true energy than apparent brightness. Luminosity tells us how much energy the star produces every second, regardless of distance or dust. For VY Canis Majoris, this means a colossal output, on the order of 10 carat 31 to 10 carat 32 watts. By comparison, the Sun outputs about 3.8 times 10 carat 26 watts. That's like comparing a flashlight to a city's entire power grid, except even that analogy doesn't come close to the true gulf in energy. Another intriguing aspect is that VY Canis Majoris is not the most luminous star known, despite its immense size. Other stars, particularly the blue hypergiants and Wolf-Rayet stars, can radiate millions of times the Sun's luminosity. The difference lies in temperature. Hotter stars radiate much more energy across the electromagnetic spectrum. VY Canis Majoris, being relatively cool with a reddish surface temperature, emits enormous amounts of energy, but it spreads that energy across a lower energy part of the spectrum. Still, its overall output makes our Sun look like a candle compared to a bonfire. So, when you hear that VY Canis Majoris is up to 300,000 times more luminous than the Sun, remember that this isn't about how bright it looks in the sky, it's about how much energy it is truly generating. It's one of those cosmic paradoxes. The universe hides its titans in plain sight, cloaked in dust and distance, waiting for our instruments and mathematics to reveal their true nature. The story of VY Canis Majoris temperature is one of those details that seems deceptively simple, yet it carries profound implications for how we understand the star. Unlike the Sun, which has a surface temperature of about 5,778 Kelvin, VY Canis Majoris is much cooler. Estimates put its surface temperature somewhere between 3,200 and 3,500 Kelvin. Now, those numbers might sound blisteringly hot compared to anything on Earth, but in stellar terms, they are relatively low. That cooler temperature is the reason VY Canis Majoris glows with a deep, ruddy hue. Stars follow a very clear pattern known as the relationship between temperature and color. Hotter stars glow blue or white, while cooler stars radiate with orange or red light. That's why Rigel in Orion shines blue-white. It burns at more than 10,000 Kelvin on its surface. By contrast, Betelgeuse glows orange-red at about 3,500 Kelvin, making it visually similar to VY Canis Majoris. The physics behind this is straightforward. Stars emit light across the electromagnetic spectrum, but the peak wavelength of that radiation depends on temperature. Hot stars peak in shorter wavelengths, blue and ultraviolet, while cooler stars peak in longer wavelengths, toward red and infrared. At around 3,200 to 3,500 Kelvin, VY Canis Majoris emission peaks squarely in the red part of the spectrum. This makes it appear as a faint red star through a telescope. But there's more to it than just color. That relatively cool surface temperature is directly linked to its hypergiant classification. When stars expand into supergiants and hypergiants, their outer layers swell so dramatically that they cool down. Imagine pulling the embers of a fire apart. The same heat spread over a larger area produces a lower temperature glow. That's essentially what happens with VY Canis Majoris. Its core is still ferociously hot, driving nuclear fusion reactions, but the immense size of its outer envelope dilutes that heat across a massive surface area, cooling the skin of the star. This cooler surface does not mean it is dim or weak. Quite the opposite. Despite having a surface temperature lower than the Sun's, VY Canis Majoris has such an enormous surface area that it still pours out hundreds of thousands of times more energy than the Sun overall. The Sun's surface may be hotter, but its smaller size makes its total luminosity modest in comparison. VY Canis Majoris is like a colossal furnace glowing red-hot, not as searing as a blowtorch, but vastly more powerful because of its scale. The redness of the star also ties into its instability. Cooler, puffed-up outer layers are less tightly bound by gravity, and that makes them more vulnerable to eruptions and mass loss. When you look at VY Canis Majoris spectrum, you don't just see the red light. It's laced with signatures of molecules like titanium oxide, which can only form in relatively cooler stellar atmospheres. That molecular presence is another clue that we're looking at an enormous, unstable hypergiant at a relatively low surface temperature compared to its hotter, more compact cousins. In fact, one of the things astronomers notice about red hypergiants like VY Canis Majoris is how their colors can fluctuate slightly. Variable stars of this type can brighten or dim as their outer layers shift and pulsate, and those changes subtly affect the shade of red that reaches us. So, while its average temperature hovers around the 3200 to 3500 Kelvin range, it isn't perfectly stable. It breathes, expands, contracts, and throws material into space, and each of these processes influences the exact look of the star. What's fascinating here is the psychological effect. To our eyes, red often feels like the color of fire and heat, yet in stellar terms, red is the cool end of the spectrum. VY Canis Majoris glows red not because it is the hottest, but because it is cooler than most stars we typically think of as bright. That flip in perspective, where red means cool on a stellar scale, is a subtle but powerful reminder that the universe doesn't always match our earthly intuitions. So when you hear that VY Canis Majoris glows red, remember, it's not red because it's a modest little ember, but because its swollen outer layers have stretched so far outward that the heat of the core can't keep them blazing blue-white anymore. It's red because it is old, vast, and unstable, a cosmic giant in its twilight. That crimson glow is the light of a star nearing the end of its story. VY Canis Majoris is not just large, luminous, and red, it belongs to one of the rarest and most extreme stellar categories known, the red hypergiants. To understand why this classification is so special, we need to zoom out and think about the family tree of stars. Most stars in our galaxy are small and relatively steady, like our Sun, which is considered a main sequence star. These stars spend billions of years quietly fusing hydrogen into helium in their cores. Larger stars, many times more massive than the Sun, live faster, burn hotter, and eventually evolve into supergiants. But even among those giants, only a handful ever reach the hypergiant stage. Hypergiants are the titans of the stellar world, existing at the very edge of what is physically possible for a star. A red hypergiant, specifically, represents one of the rarest evolutionary phases. These stars are massive enough to swell to enormous volumes but unstable enough that they're constantly shedding material into space. They are incredibly short-lived compared to stars like the Sun. While the Sun's main sequence lifetime is about 10 billion years, a red hypergiant might exist for only a few 100,000 years in this swollen phase. In cosmic terms, that's the blink of an eye. That fleeting lifespan is one reason they're so rare. Out of the hundreds of billions of stars in the Milky Way, only a tiny fraction are red hypergiants at any given time. VY Canis Majoris stands as a textbook example of this stellar rarity. It has all the hallmarks: tremendous size, cool surface temperature, intense mass loss, and instability. These qualities set it apart not just from ordinary stars but even from the more common red supergiants like Betelgeuse or Antares. Supergiants are already extraordinary, much larger and more luminous than the Sun, but hypergiants push those boundaries even further, stretching the definitions of stability and endurance. What makes red hypergiants like VY Canis Majoris even more fascinating is how they contrast with other hypergiants. There are also yellow and blue hypergiants, each representing different phases or conditions of stellar evolution. Blue hypergiants, for example, are hotter, more massive, and often more luminous than red hypergiants, but they are more compact in size. Yellow hypergiants are transitional stars, caught in between phases of expansion and contraction. Among this rare group, red hypergiants stand out because of their sheer volume. Their swollen outer layers give them some of the largest physical sizes in the universe. The rarity of red hypergiants also makes them precious to astronomers. Because they are so uncommon and short-lived, each one becomes a kind of natural laboratory for studying how the most massive stars live and die. Every observation of VY Canis Majoris adds to a very limited dataset, helping scientists piece together how stars transition from burning hydrogen to fusing heavier elements, how they shed material, and how they ultimately explode or collapse. Another factor adding to their rarity is the instability itself. Hypergiants are known for eruptive behavior. Their luminosities push them close to the so-called Eddington limit, the point at which radiation pressure from within nearly balances gravity's pull. When stars hover near this threshold, they become prone to violent outbursts, throwing vast amounts of gas and dust into space. This instability shortens their lives further, ensuring that few ever remain in this phase long enough for us to catch them. In the night sky, most of the bright stars we see are relatively normal compared to this extreme category. To stumble upon a red hypergiant is to stumble upon a cosmic oddity, something so rare that astronomers treat each one almost like a celebrity. That's why VY Canis Majoris garners such attention. It's not simply another giant, it's a stellar extreme, a rare example of a star at the very limits of what stellar physics can produce before collapse becomes inevitable. So when we say that VY Canis Majoris is a red hypergiant, we're not just giving it a technical label. We're placing it in one of the rarest, most volatile, and most spectacular categories of stars known to science. To encounter one in our galaxy is to see a fleeting moment in stellar evolution, a reminder of how diverse, unpredictable, and extraordinary the universe truly is. One of the most defining features of VY Canis Majoris is its instability. Unlike our Sun, which shines with steady reliability, this red hypergiant lives in a constant state of turmoil. Its outer layers are so distended and tenuous that they can barely resist the pressure from the furious energy being generated deep in its core. As a result, the star does not simply sit quietly in the cosmos. It erupts, it convulses, and it continually sheds pieces of itself into the surrounding space. These violent eruptions and steady outflows of gas and dust are what make VY Canis Majoris appear enshrouded in a complex, chaotic nebula. Through telescopes sensitive to visible and infrared light, astronomers can actually see the structures created by this mass loss: arcs, knots, and plumes of material stretching out from the star in irregular directions. These are not smooth or symmetrical shells like the rings of a planet or the halos around some other stars. Instead, they look like the aftermath of colossal stellar storms, evidence of repeated outbursts over centuries. Mass loss is one of the signature traits of hypergiants. Because their surface gravity is relatively weak, spread across such an enormous radius, it doesn't take much for the star to throw matter outward. Add to that the intense radiation pressure from within, and the star becomes a kind of cosmic volcano, ejecting gas at speeds of tens of kilometers per second. Over time, these outflows build a circumstellar envelope that can weigh many times the mass of Earth. In the case of VY Canis Majoris, astronomers estimate that it has already lost a significant fraction of its original mass. This is not a stable star. It is literally disintegrating in slow motion before our eyes. The nebula around VY Canis Majoris is particularly fascinating because it tells a story of asymmetry. Many stars shed material in relatively even shells as they age, but VY Canis Majoris seems to hurl its matter in lopsided bursts. Observations show vast arcs of gas on one side, clumps and filaments on another. This suggests that the eruptions are not evenly distributed, but occur through giant convective cells or localized surface events that channel material preferentially in certain directions. Imagine storms the size of our entire solar system, bubbling up from beneath the star's surface and hurling matter into interstellar space. Some of these eruptions may be tied to processes similar to what we see in smaller variable stars, like pulsations where the star expands and contracts rhythmically. But on VY Canis Majoris, the scale is far more violent. When its surface layers swell outward, they can overshoot, breaking free of the star's weak gravitational grasp. The result is an ejection event that sends gas and dust streaming away, where it cools, condenses, and becomes visible to our telescopes. Over centuries, these eruptions have carved the surrounding nebula into a kind of patchwork quilt. To astronomers, these features are more than just pretty structures, they are diagnostic clues. By studying the speed, direction, and composition of the expelled material, scientists can reconstruct the star's recent history. Each plume or arc is a time capsule, marking an outburst that happened decades or centuries ago. Together, they tell us that VY Canis Majoris has lived for generations in a state of chaotic shedding, preparing itself for its eventual demise. The violence of these eruptions also matters for what comes next. As the star loses mass, its evolutionary path is altered. A star's fate depends heavily on how much material it retains before collapse. If VY Canis Majoris continues to bleed mass at its current rate, it could lose enough to change the way its life ends, whether it explodes in a supernova, collapses into a black hole, or undergoes an even more exotic transformation like a hypernova. Its instability today is essentially shaping its destiny tomorrow. From Earth, We cannot watch these eruptions in real time. They play out over decades and centuries, but the evidence is written into the nebula. Every asymmetric knot of dust, every arc of glowing gas, is a signature of the star's instability. Instead of a serene red glow, VY Canis Majoris is more like a cosmic tempest, a star raging against itself as its outer layers unravel into space. When we focus on the gas and dust clouds surrounding VY Canis Majoris, we're really looking at the aftermath of a star tearing itself apart piece by piece. This hypergiant doesn't just shine, it sheds. Over the centuries, VY Canis Majoris has expelled an extraordinary quantity of material into space, creating an envelope of gas and dust so immense that astronomers compare its scale to small nebulae. And we're not talking about a few wisps of matter. The amount it has released is measured in terms of Earth's mass, thousands of Earth's worth of material drifting away from the star, sculpting a chaotic environment that both conceals and reveals its inner life. The material being expelled comes from the star's outer layers. Because its gravity at the surface is so weak compared to its internal energy output, VY Canis Majoris cannot hold onto its envelope tightly. Convection from deep within pushes up massive currents of plasma, radiation pressure pushes outward, and the balance tips. Instead of stability, the result is escape. Great volumes of hydrogen, helium, and heavier elements are flung into the surrounding interstellar medium. As these gases cool, they condense into dust grains, adding opacity that dims the star's visible light and re-radiates energy in the infrared. Astronomers estimate that the star has already lost a significant portion of its mass, perhaps several times the mass of our Sun, through this steady process of ejection. And if you want to bring that into planetary perspective, consider that the Earth's mass is only a tiny fraction of the Sun's. So when we say that VY Canis Majoris has hurled thousands of Earth masses into space, we're describing a mass loss that is staggering even for astrophysical standards. These aren't little puffs of gas, they are colossal upheavals that dwarf the scale of planets. The shapes of these ejections are just as fascinating as their quantities. High-resolution observations with instruments like the Hubble Space Telescope and powerful ground-based telescopes reveal arcs and clumps of gas arranged asymmetrically around the star. Instead of forming a neat, concentric shell, the material seems scattered like debris from a storm. Some of the arcs stretch hundreds of billions of kilometers away from the star. These arcs likely trace out ancient eruptions that occurred centuries ago. Other features appear more compact and recent, evidence of ongoing activity. Together, they form a chaotic halo of matter that testifies to the star's instability and violent past. Dust plays a particularly important role in shaping how we perceive VY Canis Majoris. Dust grains, formed from elements expelled by the star, absorb visible light and make the star appear dimmer than its true luminosity suggests. That's why, despite its staggering brightness, it looks faint when viewed through a telescope. But this same dust re-emits energy at infrared wavelengths, making the region glow brilliantly when studied with infrared observatories. In fact, some of our best insights into the structure of its circumstellar environment come not from visible light, but from mapping the infrared signatures of this dust. The sheer mass of gas and dust being expelled has larger implications for the cosmos as well. Stars like VY Canis Majoris are important contributors to the enrichment of the interstellar medium. The material it throws off contains heavier elements forged in its interior, carbon, oxygen, silicon, that will eventually mix with the galactic environment, seeding future generations of stars and planets. The very atoms that make up rocky worlds like Earth, and even life itself, are recycled through this kind of stellar process. VY Canis Majoris, in violently losing its outer layers, is ensuring that its legacy will endure in the material makeup of whatever stars and planets may form from its remnants millions of years from now. For now, though, the star is surrounded by a cocoon of its own making. Gas and dust clouds, shaped by ejections thousands of times Earth's mass, swirl around it like storm clouds around a raging volcano. They hide much of the star's direct light, they scatter radiation into glowing arcs, and they offer astronomers a living laboratory for studying stellar death in action. Each knot of dust is a piece of evidence, a story of instability, of loss, and of the immense power of a star in its final stages. The fate of VY Canis Majoris is as dramatic as its current appearance. A star this massive and unstable does not simply fade away like our Sun will in billions of years. Its end will be violent, spectacular, and transformative on a cosmic scale. Astronomers are certain of one thing: VY Canis Majoris will not die quietly. Instead, it will meet its demise either as a titanic supernova explosion or, perhaps even more dramatically, as a direct collapse into a black hole. To understand this, we need to revisit the physics of stellar life cycles. A star's ultimate fate depends primarily on its initial mass. Smaller stars, like our Sun, fuse hydrogen into helium over billions of years and eventually shed their outer layers to form a planetary nebula, leaving behind a white dwarf. But massive stars live far more intense, shorter lives. They burn through their nuclear fuel at an astonishing rate, progressing through a sequence of fusion stages: hydrogen to helium, helium to carbon and oxygen, then onto heavier elements like neon, silicon, and ultimately iron. Iron is the end of the line. Fusion of elements lighter than iron releases energy, sustaining the star against the crushing force of gravity. But once iron builds up in the core, it cannot be fused into heavier elements without consuming energy instead of releasing it. This creates a catastrophic imbalance. When the iron core grows too large, it suddenly collapses under its own gravity in a fraction of a second. That collapse rebounds in a ferocious explosion, a supernova. For a star as immense as VY Canis Majoris, that future seems all but inevitable. Its tremendous size and instability suggest that it is already well along in this chain of nuclear burning, building toward the day when its core will collapse. When that happens, the explosion will outshine entire galaxies for weeks, releasing as much energy in seconds as our Sun emits over its entire lifetime. The shockwave will blast through the circumstellar gas and dust, lighting up the nebula around it like fireworks on a galactic scale. But supernova is only one possible ending. Some simulations suggest that the very largest stars might bypass the traditional explosion altogether. If VY Canis Majoris retains enough mass in its core at the time of collapse, gravity may overwhelm the explosive rebound. Instead of blowing itself apart, the star could collapse directly into a black hole, swallowing its own layers almost instantaneously. In this case, much of the energy that would normally produce a spectacular light show might instead be trapped behind the event horizon, leaving only faint traces of the cataclysm for us to detect. This failed supernova scenario is an idea astronomers are actively exploring, and stars like VY Canis Majoris are prime candidates for such fates. There's even a third possibility: the hypernova. If conditions are just right, if the star's rotation and mass distribution favor it, the collapse could produce an explosion even more powerful than a typical supernova, accompanied by intense gamma-ray bursts. These events are among the most energetic known in the universe, capable of releasing unimaginable amounts of energy in narrow beams that sweep across space. If VY Canis Majoris were to end in such a way, it would become one of the most extreme stellar deaths we have ever studied. The timescale for this grand finale is uncertain, but it is measured in astronomical shortness. While our Sun still has billions of years left, VY Canis Majoris is nearing the end of its brief existence. Astronomers estimate that it may only have a few 100,000 years, perhaps less, before the inevitable collapse occurs. That might sound like a long time to us, but in the life of a star, it is nothing more than a blink. It is entirely possible that our distant descendants, if humanity endures, will one day witness the light of VY Canis Majoris' final moments sweeping across the night sky. When that happens, it will not just be a cosmic spectacle. It will be a transformative event for the galaxy. The explosion, or collapse, will seed the surrounding regions with even more heavy elements, enriching the Milky Way's interstellar medium and helping shape future generations of stars and planets. Its violent death will be as important to the cosmic ecosystem as its turbulent life has been. So, the story of VY Canis Majoris is not just about its current enormity, but about what lies ahead. Will it shatter itself in a supernova, blaze into a hypernova, or silently vanish into a black hole? We don't yet know. What we do know is that its ending will be one of the great cataclysms of our galaxy, a reminder that even the mightiest stars cannot escape the relentless cycles of birth, life, and death written into the fabric of the cosmos. If VY Canis Majoris were to take the place of our Sun at the center of the solar system, the transformation would be nothing short of apocalyptic. The sheer size of this red hypergiant would instantly erase the familiar architecture of our planetary neighborhood. To put it into perspective, VY Canis Majoris' estimated radius is about 1,400 times that of the Sun. That is not a small difference. It is the kind of scale that breaks our usual sense of size and distance. Our Sun, for all its central importance to life on Earth, is actually a fairly modest star by cosmic standards. Its radius is about 695,700 kilometers, and its light and heat sustain life on our planet comfortably at 150 million kilometers away. But if we scaled up the Sun to the size of VY Canis Majoris, its surface would swell outward with such enormity that it would engulf Mercury, Venus, Earth, Mars, and even the asteroid belt. In fact, it wouldn't stop until it reached somewhere between the orbit of Jupiter and perhaps even beyond, depending on which radius estimates you use. That means Earth would not merely be scorched, it would literally be inside the star's bloated outer layers. Imagine the implications. The place where Earth orbits would not exist as a planet circling a star, but as part of the star's burning atmosphere. The solar system as we know it would vanish into the searing plasma of the hypergence envelope. Venus, Mars, and even Jupiter would likely be swallowed whole or subjected to such intense radiation and tidal disruption that they would cease to exist as recognizable worlds. Jupiter, the giant among planets, would suddenly be dwarfed and consumed by the stellar behemoth in its center. Even beyond that engulfing radius, the conditions would be utterly hostile. The outer planets, Saturn, Uranus, and Neptune, would not escape unscathed. Though they might remain outside the swollen body of the star, the radiation from VY Canis Majoris would be thousands of times more intense than what they currently experience. Their atmospheres would be stripped, their structures destabilized, and their very existence as cold gas giants in the outer reaches of a calm solar system would be transformed into a chaotic environment blasted by stellar winds and intense radiation. The sheer brightness of the hypergiant would change everything too. At its true luminosity, hundreds of thousands of times brighter than the Sun, our solar system would be bathed in energy on a scale it was never designed to endure. Temperatures everywhere would skyrocket, vaporizing atmospheres, oceans, and rocky surfaces. Any notion of habitability would be erased instantly. This exercise in imagination isn't just about drama. It underscores the true immensity of VY Canis Majoris. To say that it is 1,400 times the Sun's radius is easy to state, but placing it inside our solar system makes that number visceral. It makes us realize that what we consider large, the Sun itself, or Jupiter, the king of planets, is utterly trivial compared to this hypergiant. Our entire solar system would fit comfortably inside its envelope, reduced to a minor detail in the star's unfathomable bulk. And yet, what's equally fascinating is that despite its enormous size, VY Canis Majoris is not the most massive star. Its mass is perhaps only 17 to 25 times that of the Sun, far less than its gargantuan radius might imply. If placed in our solar system, its physical reach would dominate space, but its gravitational pull at the distance of Earth's orbit would not be impossibly overwhelming, certainly greater than the Sun's, but not infinite. It is its size, not just its mass, that makes the thought experiment so staggering. So when we say VY Canis Majoris would extend past Jupiter if it replaced the Sun, we are really acknowledging how fragile and small our solar system is in the face of cosmic giants. Planets we think of as enormous, distances we think of as vast, all of it collapses into insignificance inside the envelope of a single hypergiant star. It is a humbling exercise in scale, showing us that even our solar system, which feels infinite when we look up at the night sky, is dwarfed by a single star in the grand stage of the cosmos. When discussing the giants of the cosmos, VY Canis Majoris is often brought up alongside a few other stellar heavyweights, names that have captured the imagination of both astronomers and the public alike. Among them are UY Scuti, Betelgeuse, and Rigel, each remarkable in its own right. Comparing these stars not only helps us understand where VY Canis Majoris stands in the hierarchy, but also reveals the staggering diversity among the universe's stellar titans. Let's begin with UY Scuti, another contender for the title of the largest star ever measured. Located in the constellation Scutum, UY Scuti has often been quoted as having a radius around 1,700 times that of the Sun, slightly larger than the typical estimates for VY Canis Majoris. This has led to debates about which of the two holds the crown as the largest known star. But there's a catch. Measuring stars of this kind is notoriously difficult, and the numbers are constantly revised as new data comes in. Some studies have since suggested UY Scuti may not be quite as large as once thought, bringing its estimated size closer to that of VY Canis Majoris. Both stars are red hypergiants, unstable and massive, and both dominate their surroundings with sprawling envelopes of gas and dust. If UY Scuti edges out VY Canis Majoris in radius, it's by a margin so fine that the two remain in close competition. Together, they represent the outer limits of how large stars can swell before gravity and physics impose their final constraints. Now consider Betelgeuse, the famous red supergiant in Orion. Betelgeuse is iconic, brightly visible to the naked eye as the reddish star marking Orion's shoulder. It is enormous compared to our Sun, with a radius about 900 times larger, yet it is still smaller than VY Canis Majoris. Betelgeuse has long fascinated astronomers because of its variability and its impending supernova fate. In many ways, it provides a more accessible laboratory for studying massive star evolution, since it is only about 642 light-years away. But in terms of scale, VY Canis Majoris makes Betelgeuse look modest. Where Betelgeuse would comfortably engulf the orbit of Mars, VY Canis Majoris stretches far beyond to Jupiter's domain. If Betelgeuse is a skyscraper, VY Canis Majoris is a mountain range. Rigel, also in Orion, offers a different kind of comparison. Unlike the red hypergiants and supergiants, Rigel is a blue supergiant, a star burning far hotter, brighter, and younger than either Betelgeuse or VY Canis Majoris. With a surface temperature of around 11,000 Kelvin, Rigel glows blue-white and shines tens of thousands of times brighter than the Sun. In terms of radius, however, it is much smaller, only about 70 times that of the Sun. Rigel doesn't compete in size. Its claim to fame is its luminosity and mass. It is far more massive than VY Canis Majoris, despite being dramatically smaller in volume. This comparison underscores an important point. Biggest doesn't always mean heaviest, and brightest doesn't always mean largest. Different types of stars achieve greatness in very different ways. In the grand contest of stellar extremes, then, VY Canis Majoris ranks as one of the very largest in sheer size, rivaled only by UY Scuti and perhaps a handful of others whose measurements remain uncertain. Betelgeuse, though smaller, captures our imagination because of its nearness and visibility, while Rigel dazzles with its heat and luminosity. Each star represents a unique corner of the stellar spectrum. Red hypergiants like VY Canis Majoris and UY Scuti that swell to impossible radii. Red supergiants like Betelgeuse that dominate the night sky with their ruddy glow, and blue supergiants like Rigel that burn with youthful, blistering intensity. Together, they remind us that there is no single measure of greatness among stars. VY Canis Majoris may take the crown in terms of sheer size, but its competitors highlight the diversity of extremes. The universe does not settle for one definition of largest or brightest. Instead, it gives us a gallery of stellar giants, each astonishing in its own way. And in that gallery, VY Canis Majoris stands as one of the most spectacular, not because it overshadows all others in every category, but because it pushes the boundaries of size to the very edge of possibility. On the vast stage of the Milky Way galaxy, with its hundreds of billions of stars, VY Canis Majoris occupies a place of extreme rarity and significance. While to us it seems impossibly gigantic, it is important to consider how it fits into the larger hierarchy of stars that populate our galaxy. Most stars in the Milky Way are far more modest, and that contrast is what makes VY Canis Majoris so remarkable. The vast majority of stars, about 70%, are red dwarfs, small, cool, and dim stars with only a fraction of the Sun's mass and luminosity. These stars are so numerous that they dominate the galactic population, even though they are nearly invisible to the naked eye from Earth. Next, we have stars like our Sun, main sequence stars of moderate size and brightness. These are relatively rare compared to red dwarfs, but they are still common enough to form the backbone of habitable systems. Moving up the scale, we find larger stars like A-type and B-type main sequence stars, hotter and brighter than the Sun but with shorter lifespans. At the top end of this hierarchy sit the giants and supergiants. Red giants are far less common than main sequence stars, and supergiants rarer still. They represent a brief, unstable phase in the life cycle of high-mass stars, which means at any given time, only a small fraction of stars in the Milky Way are in this category. Hypergiants, like VY Canis Majoris, are even scarcer, true cosmic anomalies. Out of the hundreds of billions of stars in the Milky Way, astronomers estimate there may be only a few dozen red hypergiants in existence at any one time. That means VY Canis Majoris belongs to a tiny, elite group at the very edge of what stellar evolution allows. To put this into perspective, if you were to pick a star at random in our galaxy, the chance of it being anything like VY Canis Majoris would be vanishingly small. The odds are overwhelmingly in favor of selecting a dim red dwarf, perhaps a star so faint it could only be seen with a telescope. By contrast, VY Canis Majoris is one of the largest and most luminous stars we've ever catalogued. It represents not the rule, but the exception, an outlier so extreme that it makes the Sun, which we consider immense in human terms, look like a speck of cosmic dust. In terms of the Milky Way's stellar diversity, VY Canis Majoris holds a special role. Its size places it near or at the theoretical limits of how big a star can get before collapsing under its own instability. That makes it a benchmark for astrophysical models. It's as though the Milky Way has provided us with a natural laboratory at the extremes of stellar physics, a way to test our theories against the rarest and most extraordinary data points. But the star's position in the galactic hierarchy is not just about rarity, it's also about influence. Stars like VY Canis Majoris may be few in number, but they have an outsized impact on their environment. Through their powerful stellar winds, eruptions, and eventual explosive deaths, they inject heavy elements into the interstellar medium, drive the dynamics of star-forming regions, and shape the chemical evolution of the galaxy. In this sense, hypergiants act as cosmic architects, contributing disproportionately to the recycling and enrichment of matter that will one day form new stars, planets, and perhaps even life. So in the grand hierarchy of the Milky Way, VY Canis Majoris is a rarity among rarities, an extreme giant standing on the outer edge of possibility. Most stars are small, quiet, and long-lived. VY Canis Majoris is the opposite, vast, unstable, short-lived, and transformative. It is a reminder that the galaxy is not made up of uniform stars, but of a staggering diversity, from the faintest dwarfs to the most colossal hypergiants. And in that spectrum, VY Canis Majoris marks the point where size itself becomes almost incomprehensible, a place where stellar physics is pushed to its breaking point. When we shift the scale from galactic to human perspective, the immensity of VY Canis Majoris takes on an even more humbling meaning. Numbers like 1,400 times the radius of the Sun, or billions of Earths could fit inside sound impressive, but they can still feel abstract. It's only when we pause to really consider Earth's place in comparison to this hypergiant that the true insignificance of our little world becomes clear. Start with the simplest visual, the Earth compared to the Sun. The Sun's radius is about 109 times larger than Earth's, meaning that over 1 million Earths could fit inside the Sun's volume. That alone is enough to make Earth feel tiny, a pale blue dot suspended in a solar system dominated by our star. And yet, when we then stack the Sun against VY Canis Majoris, the scale becomes nearly incomprehensible. If the Sun is already a giant compared to Earth, VY Canis Majoris is a giant compared to the Sun. Imagine shrinking Earth down to a grain of sand. On that same scale, the Sun would be about the size of a large beach ball. But VY Canis Majoris, placed alongside them, would be a sphere larger than a multi-story building. That means Earth, that little grain of sand, would not even be noticeable against the immensity of VY Canis Majoris. You could lose our entire planet, our oceans, our continents, our civilizations, all of it, inside a single convective plume bubbling on the surface of that star. Even Earth's orbit, which feels enormous when we think of the 150 million kilometers separating us from the Sun, becomes a trivial measurement in the face of VY Canis Majoris. If Earth's orbit were traced around the star, it wouldn't circle outside it, it would lie deep within its atmosphere. Our planet would be incinerated long before it could complete a single rotation. Jupiter's orbit, the boundary we often think of as the outer edge of the inner solar system, would barely skim the surface of this star. The scales we treat as immense on a human level are swallowed whole by the dimensions of this hypergiant. What's more sobering is to realize that Earth's entire history, all of human civilization, every memory, every achievement, fits on a world that is less than a dust speck compared to VY Canis Majoris. From the perspective of the universe, we are not only small, we are almost nothing at all. The mountain ranges that seem colossal to us, the oceans that feel vast, even the distances between continents, all of these vanish into complete irrelevance when compared to the size of a single star. And yet, this isn't just about feeling small, it's also about wonder. The The fact that from our tiny vantage point, on a world so minuscule compared to cosmic giants, we have developed the tools, the mathematics, and the curiosity to even measure and comprehend VY Canis Majoris is extraordinary. The very act of comparing Earth to a star so far beyond our scale is a triumph of human imagination and science. So, when we say Earth is tiny compared to VY Canis Majoris, we are not exaggerating. It is not just a matter of being small, it is a matter of being unimaginably small, of being less than a whisper in a cathedral of fire so large that our entire planet would dissolve into invisibility. And yet, standing on this tiny world, we have the privilege to look outward, to know of such things, and to feel or in the face of their enormity. Astronomers devote so much attention to hypergiants like VY Canis Majoris not simply because they are spectacular to look at or because they stretch our imagination. They are studied because they hold the keys to some of the biggest questions in astrophysics. Hypergiants are natural laboratories, extreme environments where the physics of matter, energy, and gravity collide at scales that cannot be recreated on Earth. By studying VY Canis Majoris, scientists gain insights into how stars live, how they die, and how they shape the galaxy around them. One of the most important reasons lies in stellar evolution. Most of our models of how stars change over time are built around stars of moderate size, like the Sun, or slightly larger stars that become red giants. But stars as massive and unstable as VY Canis Majoris represent a very different pathway. Their lives are much shorter, their internal processes more extreme, and their deaths far more violent. By observing them in detail, astronomers can refine theories about how nuclear fusion progresses in the cores of the most massive stars, how mass loss alters their evolution, and how these stars transition into their final stages before collapse. Hypergiants also shed enormous amounts of material, and this process raises fundamental astrophysical questions. What controls the rate at which they lose mass? Why are their ejections so asymmetric, with giant arcs and knots of gas flying off in one direction rather than smooth, spherical shells? These questions are not trivial. The way mass is lost determines how much material the star has left when it dies, and that, in turn, determines whether the star explodes in a supernova, collapses directly into a black hole, or perhaps becomes a hypernova. Without studying stars like VY Canis Majoris, astronomers would be left guessing at the endgame of massive stellar evolution. Another reason for intense interest is the role hypergiants play in galactic ecology. The heavy elements we see around us, carbon in our bodies, oxygen in the air, silicon in the rocks, iron in our blood, were all forged in stars. Hypergiants like VY Canis Majoris are especially important contributors because they release so much material into their surroundings both during their lifetimes and in their explosive deaths. By studying how this process unfolds, astronomers can trace the life cycles of elements in the galaxy, answering questions about how star-forming regions are enriched, how planets acquire their building blocks, and even how the conditions for life are seeded across space. There's also the question of instability itself. Hypergiants test the limits of stellar physics. Their luminosities push them close to the Eddington limit, where radiation pressure nearly balances gravitational pull. This makes them unstable, prone to violent outbursts. But the detailed mechanisms of those eruptions are still not fully understood. By monitoring stars like VY Canis Majoris with different instruments, from optical telescopes to infrared and radio observatories, astronomers hope to uncover the physics driving these events. Are they caused by massive convection cells rising from deep within the star? Are they linked to pulsations, where the entire star swells and contracts? Or do magnetic fields play a role in shaping the eruptions? These questions remain active areas of research. On top of this, hypergiants provide a bridge between theory and cosmic catastrophe. Supernovae are among the most energetic events in the universe, but catching a star in the final centuries or decades before it explodes is extremely rare. Hypergiants like VY Canis Majoris give us a front-row seat to the pre-supernova era. By studying its variability, its mass loss, and its internal instability, astronomers hope to develop predictive tools, signs that could tell us when a massive star is on the brink of collapse. This is not just academic curiosity. Being able to anticipate and observe a nearby supernova in real time would revolutionize our understanding of stellar death and the physics of extreme explosions. Finally, there is the simple fact that VY Canis Majoris challenges the imagination. It stretches our theories to their limits. Every observation of it, Every arc of gas in its nebula, every variation in its light, every new measurement of its size, forces us to test our understanding of physics against the reality of the universe. In a sense, it is not just a star. It is a cosmic puzzle, an ongoing mystery that compels astronomers to push their methods and instruments further. This is why astronomers return again and again to hypergiants like VY Canis Majoris. They are rare, unstable, fleeting, and extreme. And in those extremes lies the promise of deeper knowledge, not only about the stars themselves, but about the story of galaxies, elements, planets, and life. To study VY Canis Majoris is to study the edges of possibility, to see how far the universe can stretch the concept of what a star can be before it succumbs to its fiery, inevitable death. One of the most compelling reasons VY Canis Majoris captures the attention of astronomers is because it acts like a living textbook of stellar evolution, specifically in the late stages of a massive star's life. Most stars, like our Sun, follow a relatively well-understood path, billions of years fusing hydrogen into helium, then swelling into a red giant, eventually shedding their outer layers and leaving behind a white dwarf. But stars as massive as VY Canis Majoris don't have the luxury of such a quiet ending. Their evolution is fast, violent, and extreme, and the star itself becomes a kind of natural laboratory for understanding the fate of the universe's most colossal suns. VY Canis Majoris helps answer one of the central mysteries in astrophysics. How do massive stars die? While we know that they end in supernova explosions or direct collapse into black holes, the exact steps leading up to those final events are complex. A star this large burns through its nuclear fuel at a ferocious rate, fusing not just hydrogen and helium, but eventually heavier elements like carbon, oxygen, silicon, and even iron in its core. Each fusion stage gets shorter as the star evolves. In a hypergiant, the hydrogen-burning phase may last only a few million years, blink of an eye short compared to the Sun's stable 10 billion-year lifetime. By observing VY Canis Majoris in its hypergiant phase, astronomers essentially catch a star on its deathbed, in the last few 100,000 years, or even less, before collapse. What makes VY Canis Majoris especially useful for studying stellar evolution is its instability. The star doesn't just sit quietly, burning fuel at its core. Instead, it erupts, belches out massive amounts of gas and dust, and creates enormous arcs and plumes in its surrounding space. These mass loss events are more than just fireworks, they are signals of what's happening inside the star. They suggest that its outer layers are being destabilized by the tremendous pressures of radiation and convection deep within. By monitoring these outbursts, scientists can connect surface activity to interior processes, learning how the late stages of nuclear burning ripple outward through a star's enormous envelope. This, in turn, helps solve one of the biggest puzzles in stellar evolution. How does mass loss affect a star's final fate? The mass a star retains in its last moments determines whether it explodes in a supernova, collapses into a neutron star, or disappears directly into a black hole. VY Canis Majoris has already shed several solar masses of material, and continues to lose more at an astonishing rate. By tracking how quickly and how unevenly it loses mass, astronomers can refine their models of how stars cross the threshold from hypergiant to collapse. VY Canis Majoris also provides insight into the variety of death pathways. Some massive stars end as Type II supernovae, others as hypernovae, events so energetic they may power long-duration gamma-ray bursts, and some may bypass explosion altogether, imploding silently into black holes. Which route a star takes depends not only on its mass but also on how it sheds that mass, how its core evolves, and how much angular momentum it retains. Studying VY Canis Majoris gives us direct observational data to match with these theoretical outcomes. Another layer of significance comes from timing. Hypergiants like VY Canis Majoris evolve so quickly that they allow astronomers to glimpse rare transitional states. Where a red giant may remain stable for millions of years, a hypergiant's evolutionary stages may play out in mere thousands or tens of thousands of years. That means when we observe one like VY Canis Majoris today, we're seeing processes in action that, in cosmic terms, are happening almost in real time. This provides snapshots of phases we might otherwise only model on computers but rarely get to witness directly in the night sky. There is also a broader lesson here. VY Canis Majoris doesn't just help us understand how one star will die, but how the most massive stars across the universe end their lives. Every supernova we see in distant galaxies, every gamma ray burst flashing across the cosmos, every black hole that forms from a collapsing giant, they all follow patterns that we can begin to decode by looking closely at stars like this one. It's like studying a single, rare specimen to unlock the behavior of an entire species. And perhaps most profoundly, understanding how massive stars die sheds light on the origin of the universe's building blocks. The heavier elements we rely on, iron, nickel, calcium, and beyond, are born in the fiery crucibles of massive star deaths. VY Canis Majoris is a preview of that cosmic recycling process. By learning how and when it will explode, astronomers better understand how galaxies are seeded with the raw ingredients for planets and life. In this way, VY Canis Majoris is more than just a curiosity. It's a cornerstone in the story of stellar evolution. It teaches us not only about itself, but about the ultimate destinies of massive stars, the creation of the elements, and the cycle of matter that links stars, galaxies, planets, and life itself. By peering into its turbulent existence, we are quite literally looking at the script of how the universe renews itself, one giant's death at a time. When a star like VY Canis Majoris sheds its outer layers, it doesn't simply discard gas and dust into a vacuum. Those outflows ripple outward, carrying with them the seeds of future cosmic structures. In the case of a hypergiant, the scale of this enrichment is staggering. The enormous stellar winds and episodic eruptions of VY Canis Majoris have already cast many times the mass of Earth into the interstellar medium, and each eruption is a delivery of raw material, chemical elements forged in the nuclear heart of the star itself, into the galactic neighborhood. These outflows are not uniform. Instead of a gentle, spherical expansion, VY Canis Majoris has ejected giant arcs, knots, and plumes of matter stretching trillions of kilometers into space. Observations with instruments like the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, ALMA, have revealed immense clouds of gas and dust glowing in infrared light. Within these clouds are molecules such as carbon monoxide, silicon dioxide, and water vapor, along with dust grains made of silicates and metals. To us, these may sound like ordinary materials, but in the cosmic context, they are priceless. These are the raw ingredients from which new stars, planets, and potentially even life may eventually form. The enrichment process is critical to galactic evolution. The first generations of stars in the universe were composed almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. It was only through generations of massive stars like VY Canis Majoris living and dying that heavier elements, carbon, nitrogen, oxygen, silicon, iron, were introduced into the cosmic landscape. Each time a hypergiant like this one exhales part of itself, it is contributing to a chemical legacy that enriches the interstellar medium. Over time, these enriched clouds collapse under gravity, giving birth to new stars. Some of those stars will have planetary systems. And within those planets, the elements we consider essential for biology, carbon for organic molecules, oxygen for water, iron for blood and planetary cores, may be present because a hypergiant once shed them. The sheer mass loss rate of VY Canis Majoris makes this process even more profound. Current estimates suggest it loses material at a rate tens of billions of times greater than the solar wind emitted by our sun. Imagine the sun blowing away a faint breeze. Now imagine VY Canis Majoris unleashing a storm so intense that it can sculpt entire nebulae around it. Over time, this transforms its neighborhood in the galaxy, not just chemically but structurally. Its outflows create shockwaves, compressing nearby gas clouds and sometimes even triggering the birth of new stars. In this way, the violent instability of VY Canis Majoris paradoxically becomes a creative force, sowing the seeds of future stellar nurseries. The visual evidence of this enrichment is striking. Astronomers studying the region around VY Canis Majoris see a vast, chaotic nebula shaped by centuries of mass ejection. Knots of gas bigger than our solar system drift outward, glowing in infrared light. Dust grains that were once part of the star's outer layers now wander into interstellar space, destined to join the galactic cycle of matter. If one could trace the journey of a single atom expelled from VY Canis Majoris, it might one day find itself incorporated into a new star, or condensed into a planet orbiting that star, or even locked inside the body of a living organism billions of years from now. This is the paradox of death in the universe. What appears to be destruction on the stellar scale is also creation on the cosmic scale. The outflows of VY Canis Majoris represent the dismantling of a star, but also the enrichment of the galaxy. They provide the elements that make future worlds more diverse, more complex, and more capable of hosting life. Without such hypergiants, galaxies would be barren landscapes of hydrogen and helium, devoid of the chemistry required for rocky planets and the life that inhabits them. So, when astronomers study the impact of VY Canis Majoris on its surroundings, they are not merely tracking a star's decline. They are watching the universe write its next chapter. The nebulae sculpted by its outflows are not just remnants, they are blueprints for the next generation of stars and systems. In this sense, VY Canis Majoris is both an ending and a beginning, a colossal star nearing its demise yet sowing the materials for countless futures scattered across the Milky Way. The eventual explosion of VY Canis Majoris will be one of the most awe-inspiring and scientifically valuable events humanity could ever hope to witness. Hypergiants like this don't simply fade away, they end in cataclysm. When its core finally exhausts its fuel and can no longer support itself against gravity, VY Canis Majoris will collapse inward and then rebound outward in an immense supernova, unleashing an explosion so powerful that for a brief time, it will rival the brightness of an entire galaxy. From a cosmic perspective, the significance of this explosion is immense. A supernova from a star as large as VY Canis Majoris would flood its surrounding region with energy, radiation, and shock waves. These shock waves would sweep through the nearby interstellar medium, compressing gas and dust clouds and likely triggering the formation of new stars. At the same time, the explosion would scatter heavy elements, iron, nickel, gold, uranium, across space. These are elements that could one day become part of planets, moons, and perhaps even life in the distant future. The enrichment we discussed earlier in its winds and outflows would be dwarfed by the chemical bounty of its final death throes. For science, the event would be a goldmine of data. Supernovae are among the most important processes in the universe, but most occur so far away that we can only glimpse them faintly with telescopes. To witness a star as large as VY Canis Majoris explode within our own galaxy would be unprecedented. Located about 3,900 light-years from Earth, it is close enough for astronomers to observe in extraordinary detail across the entire electromagnetic spectrum, from high-energy gamma rays and X-rays to visible light, infrared, and radio waves. Instruments around the world and in space would turn toward it, recording data that could refine or even rewrite our understanding of stellar death. One of the most valuable opportunities would come from studying neutrinos and gravitational waves. When a massive star collapses, a torrent of neutrinos is released, nearly massless particles that can pass straight through most matter. These particles carry direct information from the heart of the collapse, something no telescope can see. If VY Canis Majoris exploded, neutrino detectors on Earth could capture an enormous burst of them, giving physicists a rare glimpse into the processes happening inside a collapsing core. Similarly, the collapse could ripple spacetime itself, producing gravitational waves detectable by instruments like LIGO and Virgo. Together, these signals would provide a multi-messenger view of a supernova, opening new windows into physics we cannot replicate in laboratories. But what about the risks? Fortunately, despite its enormous size, VY Canis Majoris is far enough away that Earth would be safe from direct harm. The star is not close enough to threaten us with lethal radiation. At 3,900 light-years, the effects on Earth's biosphere would be negligible. We would see an incredible light show in the sky, perhaps so bright it would be visible even in the daytime, but life on Earth would go on as normal. The only real danger would be the disruption of radio communications or satellites for a short time, caused by the flood of high-energy particles. Yet even that would be minor compared to the scientific treasure such an event would deliver. For astronomers, the explosion of VY Canis Majoris would be a once-in-civilization opportunity. Supernovae this close to Earth are rare. The last naked-eye supernova in our galaxy happened in 1604, known as Kepler's supernova, long before modern telescopes existed. To have such a nearby hypergiant collapse in our era, when we possess advanced observatories and detectors, would provide data no previous generation has had the privilege to collect. It would not just confirm existing theories but likely challenge them, forcing astrophysicists to refine models of stellar evolution, nuclear fusion, and black hole formation. And there's the added possibility that VY Canis Majoris could end not in a typical supernova but in something even more exotic. Some models suggest stars of this size may collapse directly into black holes or explode in hypernovae, events even more energetic than standard supernovae and possibly associated with gamma-ray bursts. If this were the case, the event would be of even greater significance, pushing our understanding of extreme astrophysics to the limit. So, when we consider the supernova significance of VY Canis Majoris, we're looking at more than just a cosmic spectacle. We're considering an event that could enrich the galaxy with the ingredients of new worlds, inspire a new generation of scientific discovery, test the very fabric of our theories, and remind humanity of both our fragility and our privilege. To stand on a tiny planet, watching one of the universe's titans breathe its last, and learning from its final, spectacular gift. Measuring the size of a star like VY Canis Majoris is far more complicated than simply pointing a telescope at it and comparing it to the Sun. Unlike planets, which have sharp edges and solid surfaces, stars are vast balls of plasma with fuzzy, extended atmospheres that blur into surrounding space. For hypergiants, those atmospheres are not only gigantic but also unstable, filled with turbulent flows of gas, violent eruptions, and thick clouds of dust. These factors combine to make estimating the true radius of VY Canis Majoris one of the most challenging tasks in modern astrophysics, and one of the reasons its reported size has shifted so dramatically over time. One of the primary difficulties lies in the fact that stars don't have hard boundaries. The surface of a star is defined as the point where the gas becomes opaque enough to block most of the light escaping from the interior. For our Sun, this boundary, the photosphere, is well defined and easy to measure. But for a hypergiant like VY Canis Majoris, the photosphere is bloated and extended, and it doesn't behave uniformly. Giant convection cells, each larger than Earth itself, churn across its surface, creating regions of brighter and dimmer emission. This makes its boundary fuzzy and inconsistent, more like a thick fog bank than a sharp edge. Compounding this is the presence of dust. VY Canis Majoris is shedding enormous amounts of material, and that material quickly condenses into dust grains in the cooler outer regions. These clouds of dust can obscure the star's true size, dimming some parts of its light while scattering and glowing in infrared. To an observer, the star's apparent size might look far larger than the star itself because the surrounding dust is glowing as though it were part of the surface. This has led to past overestimations of its radius, where astronomers mistook extended dust shells for the true stellar atmosphere. Even the tools we use to measure stars add to the challenge. For nearby stars, astronomers can measure angular diameter, the apparent width of the star on the sky, using techniques like interferometry. But VY Canis Majoris is nearly 3,900 light-years away, which makes its angular size minuscule, even though the star itself is colossal. Imagine trying to measure the width of a coin on the Moon from Earth. That's the kind of precision required. Early telescopes simply weren't capable of resolving such detail, so initial estimates were based on brightness and temperature, leading to values that were highly uncertain and often exaggerated. As technology improved, especially with the advent of space-based observatories and advanced interferometers on Earth, astronomers were able to refine these measurements. Instruments capable of observing in infrared, such as the Very Large Telescope Interferometer, VLTI, allowed researchers to peer through the dust and isolate the star itself from its surrounding nebula. This led to a significant revision. Early estimates had placed VY Canis Majoris at an almost unimaginable 2,000 solar radii or more, but more recent studies suggest its radius is closer to 1,400 solar radii. While still enormous, the corrected size reflects the improved precision of modern instruments and our better understanding of how to account for dust and atmospheric turbulence. Another subtle challenge is variability. VY Canis Majoris is not a static object. It's a living, unstable star undergoing constant change. Its brightness fluctuates, its mass loss events reshape its surrounding environment, and its outer layers may swell or contract over time. This variability means that there may not be a single true number for its size. Depending on when it is measured, and in what wavelength of light, astronomers might record slightly different values. A measurement in visible light might differ from one in infrared, because different layers of the star's atmosphere are being probed. All of these factors, dust, distance, fuzzy boundaries, variability, combine to make measuring VY Canis Majoris a moving target. It is not that scientists have been wrong in the past so much as they were limited by the tools and assumptions available at the time. With each technological leap, from simple telescopes to interferometers and space observatories, the picture has grown clearer. The story of measuring VY Canis Majoris is, in many ways, the story of astronomy itself, a gradual peeling back of layers of uncertainty, revealing a more accurate understanding of nature's extremes. So, when we see the numbers for VY Canis Majoris shift over time, from 2000 radii down to around 1400, it's not a sign of failure but of progress. Each revision reflects more precise tools, sharper models, and better techniques. And yet, even today, astronomers remain cautious. They know that with a star this unstable and this enshrouded in dust, the true value will always carry some margin of uncertainty. In that uncertainty lies both challenge and beauty. VY Canis Majoris is not just teaching us about itself, but also pushing the boundaries of how well humanity can measure the universe. For much of modern astronomy's history, VY Canis Majoris was thought to be not just one of the largest stars in the Milky Way, but perhaps the largest star in the entire observable universe. The numbers assigned to it in the past were staggering. So staggering, in fact, that they bordered on the unbelievable. Early estimates placed its radius at nearly 2,000 times that of the Sun, which would have made it so large that if it replaced our Sun, its outer layers would have reached all the way to Saturn's orbit. At that size, it was presented as a star truly pushing against the limits of what physics should allow, a cosmic monster dwarfing even the giants we already knew. But science is not about clinging to first impressions, it's about refining them. As astronomers developed better instruments and methods, the picture of VY Canis Majoris grew sharper and more realistic. Those earlier, inflated numbers turned out to be artifacts of observational limitations, not accurate reflections of the star's actual dimensions. The problem stemmed from several factors. For one, the star's enormous mass loss created thick, glowing dust shells around it. When astronomers first studied VY Canis Majoris through ground-based telescopes, they could not easily distinguish between the star's actual atmosphere and the infrared radiation emitted by the dust in its surrounding nebula. As a result, they overestimated the size of the star, mistaking the extended glow of dust for part of its radius. In other words, they thought they were measuring the star itself, but in reality, they were partly measuring its environment. Additionally, early size estimates often relied on indirect methods, comparing the star's brightness and temperature to theoretical models of stellar structure. The challenge with this approach is that hypergiants like VY Canis Majoris don't behave like the typical stars those models were built for. Their atmospheres are unstable, their light output fluctuates, and their structures are anything but simple. Plugging numbers into models designed for smaller, more stable stars inevitably led to misleadingly large results. It wasn't until the development of high-resolution interferometry that astronomers could finally begin to separate star from nebula. Instruments like the Very Large Telescope Interferometer, VLTI, allowed them to measure the star's actual angular diameter with far greater precision. Combined with updated distance measurements and improved atmospheric models, these observations led to a significant revision of its radius. Instead of nearly 2,000 solar radii, VY Canis Majoris was redefined at around 1,400 solar radii. Still colossal, so large that it would engulf Jupiter's orbit if placed in our solar system, but not quite the record-shattering anomaly once imagined. This change in estimates might sound like a downgrade, but it actually reflects something far more exciting: the growth of astronomical accuracy. By correcting these values, scientists not only gained a truer understanding of VY Canis Majoris but also refined their techniques for studying other hypergiants. Each correction represents a step forward in peeling away the layers of uncertainty imposed by dust, distance, and the inherent fuzziness of giant stellar atmospheres. And yet, the revisions also tell us something profound about the nature of scientific discovery. For years, textbooks and documentaries referred to VY Canis Majoris as the largest star ever discovered, its 2,000 solar radius size quoted as fact. When those numbers were revised, it wasn't a sign of failure, it was a demonstration of science at its best, self-correcting, responsive to new evidence, and constantly refining its view of reality. The star didn't shrink, our understanding grew sharper. Even with the revised numbers, VY Canis Majoris remains a titan of the cosmos, one of the largest stars we have ever found, and still a strong contender in the rankings of stellar giants. But now we see it more clearly, not through the haze of assumptions and observational artifacts, but through the lens of advanced technology and improved models. What was once thought to be impossibly huge is now understood to be extraordinarily large yet consistent with the physics of massive stars. The story of VY Canis Majoris changing estimates is a microcosm of astronomy itself. It's a reminder that our measurements of the universe are always provisional, always subject to revision as our tools and understanding evolve. Each new estimate doesn't erase the old ones, it builds upon them, part of the ongoing conversation between observation, theory, and technology. And in that conversation, VY Canis Majoris remains one of the most compelling voices, reminding us that the universe is vast, mysterious, and always just beyond our current grasp. Even with decades of study, VY Canis Majoris continues to raise as many questions as it answers. Its sheer size, instability, and violent mass loss history make it one of the most enigmatic stars in the Milky Way, and while astronomers can outline its eventual fate in broad strokes, the precise details of how it will die remain shrouded in mystery. Will it explode in a brilliant supernova visible across much of the galaxy? Will it unleash a hypernova, one of the most powerful stellar explosions possible, capable of emitting gamma-ray bursts? Or will it bypass fireworks altogether, collapsing silently into a black hole with little outward display? These unanswered questions are at the heart of why VY Canis Majoris remains a focal point of research. The most basic uncertainty lies in its mass. Measuring the current mass of a star like VY Canis Majoris is difficult because of its extended and turbulent atmosphere, combined with the enormous amount of material it has already shed. We know it began its life with a mass perhaps 25 to 40 times that of the Sun, but it has lost a great deal through winds and eruptions. How much it retains now will determine its fate. If it has lost too much, it may not have the necessary core mass to collapse into a black hole. If it has retained enough, its death could end in one of the most extreme stellar events possible. Another puzzle is tied to its instability. The chaotic outbursts we see today could be pre-supernova signals, or they could simply be part of a high-purgence turbulent life cycle. Some astronomers believe these eruptions may indicate that the star is already in its final stages, perhaps only thousands of years, or even centuries, from collapse. Others caution that hypergiants can remain in this unstable state for longer than we think, meaning VY Canis Majoris could persist in its bloated, violent condition for hundreds of thousands of years before reaching its end. Then there's the question of whether its death will produce a classic core collapse supernova or something more exotic. If the star explodes as a Type II supernova, it would be one of the most luminous events in the galaxy, temporarily outshining billions of other stars. But given its mass and instability, some scientists argue that it might instead collapse directly into a black hole without a visible explosion. In that case, much of its mass would disappear into the black hole, leaving behind only faint traces of its collapse. From Earth's perspective, this would be far less dramatic, though still scientifically significant. But perhaps the most intriguing possibility is that VY Canis Majoris could end as a hypernova. Hypernovae are supernovae taken to extremes, explosions 10 times more energetic, often accompanied by intense gamma-ray bursts. These bursts are among the brightest phenomena in the universe, capable of briefly outshining entire galaxies. If VY Canis Majoris were to end this way, the gamma-ray burst would almost certainly not be directed at Earth given the narrow beam-like nature of such emissions, but the spectacle and the data it would provide would be unparalleled. The physics of hypernovae remain poorly understood, and witnessing one in real time, especially in our own galaxy, would offer clues about some of the most violent processes in the cosmos. There are also unanswered questions about what might remain after the star's death. If it collapses into a black hole, will it form a stellar mass black hole only a few times the mass of the Sun? Or could it produce an intermediate mass black hole, a type that has been theorized but rarely observed? The nature of what follows VY Canis Majoris could reshape our understanding of black hole formation and the population of compact objects within the Milky Way. Even the timeline is uncertain. Predicting when a star will explode is one of the most challenging tasks in astrophysics. While VY Canis Majoris shows signs of instability and nearing the end, near in cosmic terms could mean tomorrow, 10,000 years, or longer. The exact sequence of events leading to collapse is still being pieced together. Its variability, eruptions, and erratic behavior all hint that the clock is ticking, but no one can yet say how close we are to the moment when it will make its final statement in the galaxy. These mysteries remind us why VY Canis Majoris holds such fascination. It is not just its size or brightness that makes it extraordinary, but its role as an unsolved puzzle sitting on the edge of stellar physics. By studying it, Astronomers are not only trying to predict the fate of one star, they are testing our broader understanding of how massive stars live and die, how black holes form, and how the most extreme explosions shape the cosmos. The unanswered questions are not signs of ignorance, but invitations to discovery, and VY Canis Majoris remains one of the most intriguing invitations the universe has ever extended. When we pause to reflect on VY Canis Majoris, what comes rushing in isn't just the astrophysical data, the radius, the mass, the instability, but a sense of overwhelming humility. Standing under the night sky, looking up with our naked eyes, we see only points of light, delicate and faint, scattered like jewels on velvet. But behind that faint red dot, invisible to the human eye, lies a star so vast that it makes our sun, a blazing furnace that gives life to Earth, look like a speck of dust. This gap between appearance and reality reminds us just how limited human perception is, and how much greater the universe is than anything we can fully grasp. To put it into perspective, the Sun feels immense to us. Its diameter is about 1.4 million kilometers, and if it were hollow, more than 1 million Earths could fit inside. That fact alone is staggering. Yet, when we place the Sun beside VY Canis Majoris, the comparison almost dissolves into absurdity. A star with a radius 1,400 times that of the Sun means we could line up hundreds of suns just to stretch across its surface. If it were to replace the Sun at the heart of our solar system, Mercury, Venus, Earth, Mars, and even Jupiter would be engulfed within its bloated, fiery body. Suddenly, all of human history, culture, and existence, all the things we hold dear, wouldn't even register as a noticeable detail against such a cosmic backdrop. That is the humility stars like VY Canis Majoris force upon us. They remind us that no matter how advanced our technology becomes or how far our civilizations grow, we are still tiny inhabitants of a small rocky planet orbiting a relatively average star in a quiet corner of one galaxy among trillions. The very act of studying VY Canis Majoris, squinting across 3,900 light-years to understand the life of a star, makes us confront the staggering scale of reality. Each new observation becomes a mirror that reflects our smallness back to us, but also illuminates our unique role as creatures capable of contemplating that smallness. Cosmic humility does not diminish humanity. Rather, it enriches us. Knowing that stars like VY Canis Majoris exist, knowing that there are objects in the universe that make even Jupiter and the Sun look insignificant, stretches our imagination and sharpens our sense of wonder. The universe does not revolve around us, it does not even notice us, but the fact that we can notice it is extraordinary. Our awareness of stars like VY Canis Majoris connects us to the cosmos in a way that transcends size or power. It also helps us reframe our everyday struggles. Against the scale of a star that could swallow the entire inner solar system, our arguments, boundaries, and ambitions shrink to their proper size. They are still meaningful to us, because we live within them, but the cosmos gently whispers, there is more, there is always more. Stars like VY Canis Majoris give us perspective, not to make us feel irrelevant, but to remind us of the vastness we are part of. In this light, our smallness is not a curse but a gift, proof that we belong to something far greater than ourselves. When Carl Sagan once said we are star stuff, he was not being poetic for its own sake. Stars like VY Canis Majoris literally forge the heavy elements in their cores and scatter them across space through eruptions and eventual collapse. Our bodies, our planet, our oceans, the iron in our blood, all of it owes its existence to titanic stars that lived and died long before the Sun was born. To reflect on VY Canis Majoris is to reflect on the fact that we are made of cosmic debris from such giants, that our very atoms were once part of the same processes that now fuel this red hypergiant. Cosmic humility, then, is not just about realizing our smallness, it is about recognizing our kinship with the stars. And so, when we think of VY Canis Majoris, we don't just think of a giant red hypergiant in the distant constellation Canis Major. We think of it as a reminder of scale, of perspective, and of connection. Its immensity does not crush our significance. It enhances it by showing us that even in a universe of such unimaginable enormity, we are capable of awareness, reflection, and curiosity. That is our strength, not size, not power, but the ability to wonder. And nothing inspires wonder quite like a star that dwarfs even our Sun into near invisibility. There is something profoundly moving about the fact that we can study VY Canis Majoris at all. This star sits nearly 3,900 light-years from Earth, in a region of space our species will never visit in person. Its light began its journey long before the rise of human civilization, traveling across millennia through the vast emptiness of space, only to arrive at our telescopes today. When we look at VY Canis Majoris, we are not seeing it as it exists right now. We are seeing it as it was nearly 4,000 years ago, at a time when ancient civilizations on Earth were just beginning to carve their place in history. The very idea that we can peer so far back in time, using nothing but photons that have crossed the gulf of space, inspires a sense of awe that science alone can deliver. What makes this even more staggering is the challenge of extracting knowledge from that faint trickle of light. VY Canis Majoris is not visible to the naked eye, even though it's intrinsically hundreds of thousands of times more luminous than the sun. Dust, distance, and its faint red glow render it invisible to casual stargazers. So how do we know anything about it at all? The answer lies in the ingenuity of human science and the patience of generations of astronomers who have coaxed secrets from the cosmos using instruments of increasing sophistication. Every photon that reaches us carries a fingerprint of the star's properties. By dispersing that light into a spectrum, astronomers can measure its temperature, its chemical composition, and even the speed at which gases are moving in its outer layers. By studying subtle changes in its brightness, they can track its pulsations, its instability, and its eruptions. By using interferometry, they can measure its apparent size with precision down to tiny fractions of an arcsecond, equivalent to measuring the width of a human hair from miles away. Each of these methods demands extraordinary care, precision, and technology, and yet together they allow us to paint a picture of a star that no human eye will ever directly behold. The awe is not only in the technical challenge, but also in the artistry of inference. Imagine trying to reconstruct the shape, size, and life story of a mountain you will never climb, based only on echoes, shadows, and reflections. That is the task astronomers face with VY Canis Majoris. They must piece together its biography from fragments of evidence carried across space. And yet, they succeed. The more data we gather, the more we refine our understanding, not only of this one star, but of the entire class of hypergiants to which it belongs. There is also a quiet poetry in knowing that the data we study today is ancient light. The eruptions we observe may have happened when the pyramids of Egypt were being built, or when humanity was first inventing writing. By the time the light reaches us, the star may already have changed, or perhaps even exploded, though we won't know it until the light of that final act arrives. In this way, astronomy forces us to reckon with both time and distance on scales that defy everyday experience. To study VY Canis Majoris is to stretch the human mind across thousands of years and trillions of kilometers, bridging the unfathomable with the tools of reason. And yet, even with all of our modern instruments, uncertainties remain. Measuring its size is still difficult. Predicting its future remains elusive. Dust clouds complicate every observation. But rather than diminish the experience, these challenges only heighten the sense of wonder. Science is not about having all the answers immediately. It is about the pursuit, the process, the thrill of discovery. In VY Canis Majoris, we see not just a star, but a grand cosmic puzzle, one that reminds us of the limits of our knowledge and the joy of pushing against those limits. The awe we feel is not unlike standing at the edge of the ocean at night, hearing the waves crash in the dark, knowing the sea stretches endlessly beyond what we can see. Except in this case, the ocean is the universe, and the waves are streams of ancient light lapping against the shores of our detectors. To stand on Earth and study VY Canis Majoris is to stand at the frontier of human curiosity, staring across light years into the fiery heart of a star so vast it defies imagination, and realizing that against all odds, we are beginning to understand it. The story of VY Canis Majoris is more than the tale of a single colossal star. It is a window into the vastness of the universe and the endless journey of discovery that lies ahead. For centuries, humans have looked to the night sky and wondered what secrets it holds, and with each advance in science, we've peeled back another layer. We have learned that stars can live lives far more dramatic than our sun, that they can swell to sizes that swallow planets whole, and that they can end in explosions so violent they reshape the fabric of space around them. And yet, every answer we find seems to lead to more questions. If VY Canis Majoris, a faint, reddish dot hidden behind clouds of dust, can turn out to be one of the largest stars ever found, what else might be waiting in the shadows? Could there be stars even larger, lurking farther away, cloaked in dust and distance? Are there hypergiants in distant galaxies whose radii stretch even beyond what we think possible? Could there be exotic stars or stellar corpses unlike anything we've yet imagined, waiting for new generations of telescopes to reveal them? Astronomy thrives on this sense of the unknown. With each technological leap, whether it was the invention of the telescope, the use of space-based observatories, or the arrival of interferometry, our picture of the cosmos has grown richer and stranger. The James Webb Space Telescope and other next-generation instruments will peer deeper into the universe than ever before, potentially uncovering new hypergiants, new nebulae, and perhaps even more astonishing extremes of stellar evolution. VY Canis Majoris may be extraordinary, but it is also a reminder that the universe is never done surprising us. And beyond the stars themselves, there is the broader implication. The more we discover about the universe, the more we discover about ourselves. We learn where the elements in our bodies come from. We learn how fragile and precious Earth is compared to the cosmic scale. And we learn that curiosity, the simple act of asking questions, is one of humanity's most powerful tools. It is what brought us from gazing at the sky with naked eyes to building machines that can decode the light of stars thousands of light years away. So, as we reflect on the enormity of VY Canis Majoris, we are left with both awe and anticipation. Awe at what we already know, that a star can grow to such proportions, live in such turmoil, and one day die in such violence. And anticipation for what we do not yet know, for the discoveries waiting beyond the reach of today's instruments, discoveries that will one day redefine our place in the cosmos yet again. If VY Canis Majoris can stretch the imagination this far, then what else might be out there, hidden in the dark, waiting to be seen? What colossal stars, strange galaxies, or exotic phenomena remain just beyond the horizon of human knowledge? The sky above us is not just a ceiling, it is a frontier, an invitation written in starlight. So the next time you look up at the night sky, remember, somewhere in the constellation Canis Major, across thousands of light years, a giant star is burning through its final chapters. And beyond it, countless others await discovery. If VY Canis Majoris is this large, what else might we still discover out there? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.